Welcome to this course on mastering data ingestion for data engineering. Learn to tackle common pipeline features like schema changes and API limits by adopting the mindset and practices of a senior platform engineer. This course covers essential techniques including extracting data from APIs, automatic schema management, incremental loading, and orchestrating scalable automated workflows using modern tools. Alexey and Adrian are the data scientists who created this course, and DLTHub.com provided a grant to make this course possible.
Hi everyone, welcome to our course about the basics of data ingestion for data engineering. My name is Alexey and I have been in the software industry since 2010. Last 12 years I focused on data and creating data pipelines. I am the founder of Data Club, which is a community of people who love data, and there we teach free courses. One of these courses is Data Engineering Zoom Camp, a 10-week-long bootcamp about getting started in data engineering. I am the instructor for the first part of this course. Here we will cover the basics of data engineering. Specifically, we will talk about things like data pipeline, data ingestion, ETL, and I will also talk about extracting data from APIs and putting it to a data warehouse. In the second part, we will talk about DLT, the standard tool for data ingestion. It will be covered by my co-instructor, Adrian. Let's get started. You've built a data pipeline. The script works, everyone is happy, the data flows, reports update, everything looks great, until one day you come to work, only to realize that the job failed. You start investigating why, turned out that the schema changed, and now the script no longer works. Or API requests hit rate limit, and your script fails because there are no retries, and this leads to entire job failing. And the script you wrote using AI is now a spaghetti mess, and nobody wants to maintain it, and suddenly the entire engineering team is firefighting instead of creating new data pipelines, instead of creating new reports, and nobody is happy and nobody trusts your data. If it sounds familiar and you want to avoid situations like that in the future, this course is for you. And the reality is that most engineers can write a script that moves data from A to B, but the scripts are not always reliable. Senior engineers think ahead, they design for resilience, scalability, and automation. In this course, you'll learn how to deal with situations like that. This course is not about basic ETL. It's about approaching ingestion like a senior platform engineer, so that you can build data pipelines that work, that are resilient, even when things around them change. You already have a picture of what may happen if you ignore best practices. You spend more time fixing than building new data pipelines. Data breaks unexpectedly, leading to trust issues. The management no longer wants to use your dashboards because they don't trust the data in these dashboards. Your team avoids your pipelines because the code there is not reliable. It's not easy to understand, it's not easy to maintain, and scaling these pipelines is painful and it requires constant refactoring. So this is not a fun situation to have, and senior engineers don't want these situations to happen. They design ingestion pipelines that work now and in the future, even when things change. And this is exactly what we will talk about in the course. So this course is for analytics engineers, people who want to ingest structured and unstructured data, handle schema evolution, enable self-service analytics. This is also for data engineers, junior and mid-level, who want to move beyond creating scripts to building production-ready data pipelines, who want to automate data ingestion and scale efficiently. This is also good for analytics managers and architects who want to design reliable, scalable, and cost-efficient ingestion for analytics, machine learning, and operations. By the end of this course, you'll go from moving data from A to B to engineering ingestion systems. So you're not just reacting to failures, but preventing them. In this course, you'll learn the following. So first of all, we will learn extracting data from APIs and handling API challenges. So we will work with web services. So we will need to handle situations like authentication, rate limits, pagination, in order to extract data efficiently. Then we will also cover schema management and automatic normalization. We will use DLT to infer schema from the JSON data. Then we will flatten nested JSON. We'll extract list into children tables, and we will see how to handle schema evolution automatically. We'll also look at incremental data instruction and state tracking. When our jobs need to reprocess the same amount, when our jobs need to reprocess the same data over and over again, this is not effective. So we will learn how to load only new or modified records and thus avoiding unnecessary reprocessing. Then we will see how to load data into various destinations. So first we'll look how to store data in DuckDB, but then we'll move beyond DuckDB and store data in data warehouses such as BigQuery, Snowflake, or Data Lake. And all of that will happen automatically. Finally, we will talk about automating and orchestrating pipelines. We will deploy, schedule, and maintain ingestion workflows with tools like Dagster, GitHub Actions, and cron jobs. And finally, we will also talk about scaling data pipelines efficiently. We will see how to handle large-scale data ingestion while optimizing for performance, retries, and parallel execution. By the end of this course, you will not just know data ingestion. You will be able to build an API ingestion pipeline that automatically detects schema changes, retries intelligently, and scales with demand. If you've been in data science or analytics, you know that you usually have a clean data set that you can use. Somebody prepared this data set, like you have a table with all the columns you needed without any data issues, like you don't have any data duplicates. And what you do is just take this data and train a machine learning model on top of that, or you build some analytics on top of this data. But the reality is that this data does not just magically appear in your data warehouse. Somebody has to process this data, has to make it available, and has to clean this data such that you as a data scientist or data analyst can use it for your job. And in this particular case, the data that data scientists or data analysts use is already well structured. There is an explicit schema, and we can use this data immediately. So examples could be Parquet, Avro, database tables, and so on. But usually, as we know, the data does not just magically appear there. Somebody has to put it there, and usually the source data is raw. It's not clean. It doesn't have schema. It can be JSON file, it can be CSV files, it can be some raw logs from our server. So somebody needs to process this data, normalize it, and sometimes aggregate and then put it to our table. Here in this course, we will learn how to be the magicians who take the raw unstructured data and turn this into well-structured data. So we will be the one making data sets magically appear. And in order to do this, we need to extract data from various sources, APIs, databases, files, then normalize this data by transforming, cleaning, and defining schemas, and finally load this data to the place where it can be used, data warehouse, data lake, or database. And we usually call this entire thing data ingestion. So the process of turning unstructured data into structured data, this is what we call data ingestion. So we extract data from a source, transport it to a suitable environment, and prepare it for the use. So usually it includes multiple steps. So first we extract data from the source, then we normalize data, then we clean it, we remove inconsistencies, duplicates, we add metadata such as schema, or maybe we need to look something up. And then finally, we'll load the data to a data warehouse or some other environment where it's ready to be used. And people who take care of this process are data engineers, and they're extremely important in this process. So the data engineers are the architects behind these pipelines. They don't just build pipelines, they make sure that they are reliable, efficient, and scalable. So when they know that data scientists and analysts expect the data, they make sure that data happens and that the end users can trust this data. Beyond pipeline development, data engineers need to think about the use case and select the best storage for keeping the cost low and performance high, because every use case might be unique and we need a specific data storage for this specific use case. They ensure data quality and integrity. There could be some duplicates in the data source that need to be handled. There could be some inconsistencies that need to be removed. There could be some missing values that need to be added back to the data set. Then also it's important that only people who are supposed to access the data can access it and that others cannot. So this is called data governance, and data engineers need to also think about that. So they need to implement governance for secure, compliant, and well-managed data. So the role of the data engineers is to manage the entire data lifecycle from collecting to consumption. Now we want to extract the data. We have two options. We can process it in batches or we can process it in streaming. When it comes to streaming, when event is generated, we'll want to process it as soon as possible. So we are processing data continuously as it arrives. In case of batching, we let events accumulate and we process it periodically. So it could be every 5 minutes, every hour, every day, or every week. So batch processing is good for scheduled tasks, and stream is ideal for real-time processing use cases. Choosing the best approach depends on factors like data volume, latency requirements, and system architecture, but typically the latency requirement is the most important one. Do we have to process data immediately as soon as it arrives, or we can wait for some time before we do this? In this course, we will focus primarily on batch processing, as this is the most common way of processing data. We'll briefly touch on streaming, but the majority of applications in real-world data engineering are batch. Batch processing is best when you can wait for data to accumulate before we process it, and we process it in large chunks. So it's more cost efficient and works well for non-time sensitive workloads. So for example, we want to update a database during the night, or we want to generate daily or weekly reports. When it comes to streaming, we want to process data in real time or close to real time with minimal delay. Common use cases for streaming include fraud detection. We don't want to wait till fraudsters do anything bad to our system. We want to catch them immediately as soon as possible. And there are many other applications, like for example, in IoT, when we have some sensors attached to our production devices, and if something happens to the devices, we want to detect this as soon as possible. And there are, of course, many other use cases. And when we want to select between batch and streaming, first of all, think about latency. So if we can wait minutes, hours, days, then we need to go for batch. If we cannot wait, so we talk about milliseconds or seconds, then it's streaming. And with streaming, it's continuous small events, while in batches, it's usually a chunk of data, so it's way larger. So it's not individual events. Use cases for batch include generating reports, ETL jobs, and stream processing is about real-time analytics and event-driven applications. When it comes to complexity, streaming applications are not easy to maintain, so it requires a complex event-driven architecture, while batch jobs are easier to manage. And when it comes to cost, usually batch processing is cheaper because we already know what kind of servers we need, and we can provision these servers just for the time of the job. While for stream processing, we need our applications constantly up and running, which results in higher cost for always-on processing. There are many tools on the market that can support both batch and streaming. So first, there are tools that are specifically designed for streaming or more designed for streaming. So these tools are Apache Kafka, RabbitMQ, AWS Kinesis, Google WhatsApp. Of course, we can do some batch workloads there, but people usually use it more for event-driven architectures. And there are tools for building pipelines, tools like Apache Spark, dbt, Flink, Nifi, AWS Glue, Google Cloud Dataflow, and DLT. So these tools, some of them work better with streaming, some of them work better with batch, but many of them can handle both, so you can choose whatever tool you want. In this course, we will focus mainly on DLT. So this is the standard tool for data ingestion, so it can automate API instruction, incremental ingestion, schema evolution, and it works with both batch and streaming pipelines. Okay, now let's go to the practical part. So we talked about processing data in batch versus streaming approaches, and imagine that we want to extract data from an API data source. When it comes to batch, when we use Python, we can use the request library to send a GET request to our API and then get back the response, process this, and put these results into a data warehouse. So the use case we have for this course is the events that we have from one of our repositories. This is our course about data engineering Zoom Camp. And every time something happens in this repository, somebody starts a repo, somebody forks a repo, we see this in this endpoint. So the endpoint is /events, right? So these are all the events we have here. So we see the fork event. If we scroll down, we will see a watch event, This API is well documented. We can see all the event types. So for example, watch event is when somebody starts a repository, but we can see that there are many other events that we can have here, this API, that this API returns. So what we want to do is we want to visit the URL and we want to send a request to this URL. We want to send a GET request to this URL. It will return this JSON and we want to process this JSON. So we'll use the request library. I'm going to start by importing it. And then I'm going to send a GET request to this URL. First, let me name it a URL. And then requests.get. And then we get the URL. We'll save this to response. And since we know that this is JSON, we can type response to JSON. And then this way we send a GET request to this API, we get back the results, and we display these results. So we see this is the same data as we have here. I am going to hide it. And this is how we get data for batch processing from APIs. We see that the protocol here, HTTPS, it could be HTTP or HTTPS. And we typically send a GET request, we get back some responses, and then we do something with these responses, for example, putting them to a data, processing them, putting them to a data warehouse, and building some analytics on top of that. When it comes to streaming, it looks a little bit different. So I'm not going to live code it right now. I just want to give you a short example. So here, instead of sending a GET request, we subscribe for events in this stream. So usually the URLs that we have for streaming APIs, they start with WSS protocol, which is WebSockets. And then you define a listen. You say every time that there is a new event, I want to do something with this event. So it could be putting this event to a Kafka stream or, I don't know, reacting somehow to this event. So this is how typically it looks like. And we will not focus on this part here in this course. Okay, we have seen how to send a GET request to get the data from an API endpoint and how to, we haven't processed it yet, but we have seen some data that now we can process. But that's not the end of the story. So we cannot just send a GET request, get the data, and assume it will work like that forever. There are some challenges with extracting data from APIs. And the common challenges are, first of all, there could be some authentication involved. So when there are some endpoints that are restricted, only people who are supposed to access it can access it. So we need to tell the API that, yes, we can do this. And this usually requires a different authentication mechanisms, like including API keys and so on. Then the events that this endpoint returns, this is actually not all the events. So if we can see that the last event is from the 6th of May, from the 6th of March, but there were events before that. How can we access that? How can we access this data? So for that, we need to use the concept of pagination. We need to be able to access holder data. Then there could be also rate limits. If we start bombarding this API with requests, requesting the same data over and over again, at some point they will say, hey, slow down, you're sending too many requests. We cannot handle this request from your side. And they will just start returning an error code instead of actually returning the data. So we also need to take into account, and if something like that happens, we need to slow down and come back to requesting the data again later. Or could be some network failures. For example, something between the computer where the job is running and the server, the connection is interrupted and we cannot request the data anymore. So then the network, the API, the URL becomes unavailable for some time and we need to retry later to be able to access this data. And finally, there could be some memory issues. When the API returns so many data points that we cannot process at once, we need to gracefully handle the situation and perhaps introduce chunks and not process all the data at once. So we need to keep in mind all these things when we deal with APIs. And some APIs, some of the API developers, they are actually kind enough to provide a special URL where we can see what are our current rate limits. So for example, in the case of GitHub, they have a special endpoint rate limit, and we can see what are our current rate limits by sending a GET request to this endpoint. And then when we do this, we can see that, okay, so these are our limits. So we have 60 requests. There are 59 remaining requests, and the reset of the rate limits will happen at this particular time point, right? So, for example, we can then access this rate remaining. So this is how we can see, okay, we have 59 remaining requests, and I'll call it remaining. And for example, if we hit the rate limits and we need to handle this situation. So typically when it happens, we need to sleep for some time. So for example, we can wait for 30 seconds before retrying. And so for example, in code, it can look like if remaining equals 0, then we sleep for, let's say, 30 seconds. And of course, we need to import time for that. So this is how we can handle a situation like that when we are running out of, when we're hitting the rate limits. Then in addition to rate limiting, we can come across authenticated endpoints that require me to prove that it's actually me who is running this request. So an example again from API is /endpoint user. So if I try to send a request right now to this endpoint, then we'll see that it responds with 401 error code. So here we actually see, if we look at the request, it says it requires authentication, and here's documentation about that. So this is this endpoint is not. It's not possible to use this endpoint without a proper API key. And I already have an API token that I can use. So I went to my GitHub settings and I generated an API token. So this API token is stored here in the secrets. So I can use this token now. And right now I'm running on Google Colab. So in Google Colab, I can use this user data to access the token. But if you're using it elsewhere, if you're running your code elsewhere, you can use environment variables for that. So we have the API token, and the way we authenticate is we include this token in our headers. So there's its authorization, and then the standard way of doing this is including this into the header like that. API token. And when we send a GET request, we include this in the request. So now this is my token, and we see all the information about me. This is how we deal with authorization. And the last thing I wanted to talk about here is pagination. So here we see that this is definitely not the last event that we generated, or that was generated in our repo. If we want to access the events before this date, we can specify the get parameter page, and say, okay, we want the second page, and then this way we can go back to see all the events. Right? And this way we can iterate over different pages, and like, for example, this page 10, yeah, we can iterate over all these pages and collect all this data and process as we need. This is again the same URL. We use a GET request to send data to this URL. And right now, if we want to understand what is, okay, we send the request to this page. I'll send the request to this page. So it returns some JSON data, and we wanted to understand what is the next page for this. And the developers of this API, they include this information in the headers of the response. So we can see that there is a link header. I can access this header here. We see that for this particular request, for this particular endpoint, the next page is, this is how we access the next page, by adding the parameter page equals 2. And there is also the last page, page number 10. Right? So now what we can do is we can iterate, we can have a loop, and then every time we send the request, we'll see, okay, what is the next page? And this way we process all the events until we reach the last one. And for example, if we actually send the request for the last one, it looks a bit different. So there is no next link here, there is only previous link. So what we can do is we can just check if next is there in the links, and if it's there, we take the link, we send another request, and we keep doing this until there is no next. Then this thing is not actually easy to parse. We can parse it because there is structure, but we don't want to parse it ourselves. And the requests library already does this for us. So we can just access links by using links there. Yeah, let me check a different page. So if we do it page number 9, we have the next link. So what we do is we check if next is there among all these links, and if it's there, next, if it's there, we just access the URL. So, and we keep iterating until we get all the pages we need. So let us implement that. So I'm going to have a while loop, while true. So we will do it forever, and we'll break inside the loop. So here I want to check if next is not in response links, then we break the loop. But if it's there, we'll get the URL. And the URL is, this is how we actually access it. Right? So in this way, we send a GET request and we get the new URL, and we keep doing this until there is no next link. And now we can do something with the response. So for example, I can do the length of the data, and data would be in this case response.json. So let me execute this. Yeah, of course I need to start with event num with the first page. And we see that it has, each page has 30 events, except the last one, which has 22. So, and 10 pages in total. So this is how we process, this is how we handle pagination. In case of APIs, yeah, so different APIs, different API providers handle the situation a little bit different. So in this case, in case of GitHub, we get it from the header information from the links section. Some may explicitly return this in the response, and we need to adjust our code to each of the API providers. Okay, so now we know how to handle pagination, and let's say we want to process all this data. We want to take all this data and put this to our data warehouse. So we can run a script like that, and simply append this to a list. And then at the end, once we collect all this data, we load this to a data warehouse. This could be problematic if we have a lot of pages. In this case, we have just 10 pages, but what if we had 1,000 pages and each page contains not 30 items, not 30 events, but a million events? Then we will quickly run out of memory, our job will crash, so we will need to do something about that. Instead of collecting everything at once and then processing, we can do this in chunks. And since this API already kind of chunks the events data, we can, for example, we can process one page at a time. And for that, I will take the code we have already written and modify it slightly. So we will write a special function that we'll call events getter. And here, when we get back the data, so this function events getter is actually a generator. So it will return every time we request a new page, it will return this. So instead of accumulating this in a list and returning everything, we use the yield keyword to actually, at the moment when the page is ready, we immediately return. And the client, like whoever is using this function, will process this one page at a time. And so now I'm just going to use this generator here. I'll call it events pages. And we can iterate over these pages. And for example, we do some logic here. Right now, I'm just going to print it, but this is where we do some processing. And now we send a GET request for each of the pages, and instead of accumulating all the pages, we process them one at a time. Okay, so we know now how to request pages. We talked about all the possible issues that might arise, and now we are ready to actually do something with this data, because we cannot simply take this data set as is and insert it, load this into our data warehouse. We actually need to do something, because in our data warehouse, we have tables, and this is JSON. JSON is unstructured. So we have nested fields here. So for example, actor is a nested field. And in order to put this into a table format, in order to convert it to a table format, we need to, we call this process unnesting JSON fields. So this is one of the things we can do. There are other things. So we often have a situation like we have lists in the requests. So for example, here we have a list with topics. This is for a pull request event. We have some topics, right? And we need to also be able to do something with this to also flatten this list. And there are many other things. So we can add types, we can rename columns, like all these things are important when we are converting data from the raw format to tabular format when we want to load this to a data warehouse. And this is, let me take a look at one of the events that we have. I'll take events page. So this is our event. And right now we want to write some code that processes this event and flattens it. So I will call this function process event. Well, let me just print it one more time. So this will be the function that is taking the raw event and returns an event that we'll later put in our data warehouse. So we'll start with an empty dictionary. And right now, we first will just copy some of the fields that do not need any preprocessing. So this is first of all ID. So this is this thing. Then type. So for ID, we simply copy it as is without any changes. And then we do the same with type. With public. And we've created that. So we simply take these events, we take these fields as they are without any extra preprocessing and return them. And then we want to do something with actor. So actor is a nested JSON field. We need to do something about this. So we want to access ID and let's say login. And here we use the special naming convention. So when we access, when we normalize the data, so the naming convention is actor __ ID, meaning that actor was a nested field, and we say, okay, it was a nested field, and the field inside this actor is ID. And in Python, this is how we access it. Right? So it's a dictionary inside a dictionary. And we also want to copy the login. And now we simply return the result. Let us quickly test it. So I'm going to use this function on the event. Okay, so this is how we convert the original event that we had into a processed event. So I'll call it processed event. And then of course we can use this function for all the events we have in our batch, in our page. So I'll just do a for loop for event in events page. And then let's say we can accumulate all these events into a list that I will call processed events. Okay, and now at the end we just simply can see what is inside. It contains all the events that we have, but they are already processed. So they are normalized. And here we created add as is. We didn't do any changes, but actually we can parse this too. So this is it's stored in a special ICO date time string. And let's say we want to parse this string and store it as a Unix timestamp. So we can do this. Right now, we will take our function. So let me find this. We'll take our function for processing events and we'll adjust it. And here, yeah, I already imported datetime, and in case of Python, we can use this from ISO format function for parsing the data. So called parsed timestamp. And I can now extract the Unix timestamp from this using the timestamp field. Yeah, so when I do something like that, and we can immediately check how it looks like for our events. Sorry. Okay, now we can see that the created add field in the processed event looks like that. So right now it's a Unix timestamp. Okay, and then there is another thing we talked about. So here we want to extract these topics. And these topics, the structure it's quite nested. So topics live inside, we'll see inside repo. And then repo is inside base. Then this is inside pull request, and pull request is inside payload. So this is super nested. And what makes the matter even more complicated is not all the events actually have this. So we want to be careful and or what we are going to do right now is I'll just use the get function of a dictionary, and I'm going to get the payload. And if the payload field is not there, I'm simply returning an empty dictionary. And then from payload, it's pull request. Again, empty dictionary if it's not there. Then base. Then repo. And then finally topics. And if again topics is empty, then we return an empty list. And let us just return topics. Now I can do this for all the data, for event and for all data. Process event, and yeah, we will put them inside processed event list. We have already written this. But also now we need topics. So I'll call this processed topics. And topics. And what we're going to do is we're going to extend this list with topics. Extend topics. And then, of course, yeah, we append to the events. Or we append to processed event. So now we can see, we can just print both of them. Yeah, it's, I guess, too much. Let's just look at first 5. And I'm going to actually print them. So now, yeah, we see that these are our events and these are our topics. But as I said, we actually need to be able to link back the topic to the event. And for that, we need to have the ID. We need to use the ID as the reference. So it means that we need to do a bit of extra processing for topics, which I'll do inside here, inside this function, topics. So have a variable called processed topic, which will be a dictionary. First, we'll have event ID, which is the ID. And then topic name, which is the topic itself. So now when I do this, yeah, of course, I need to also put the results to process topics because we don't say them. Yeah, now it looks much better. So now for each of the topic, we know what is the corresponding event ID. So we have 2 lists. Each of them contains dictionaries, and these dictionaries is what we are going to put inside a data warehouse. Okay, so we prepared all the data. This data is in these 2 lists, process events and process topics. Now they contain the dictionaries with the cleaned event data, cleaned topics, and now we're ready to load this data into a data warehouse. So let us do that. As a data warehouse, we would use DuckDB, which is a simple in-memory database that we can use. And this. Okay, so first we create a connection to a DuckDB database. And this will create a file, GitHub events.db. Next. Next, we will create the GitHub events table. And if we look at our event, so if I look at processed events, we have these fields. We have ID, type, public, created, add, actor ID, login, actor login, right? And we have all these fields here. So there is one-to-one mapping between this dictionary and table. And yeah, here are the types too. So now we want to insert all these processed events in this table. So we have all these events. First, we need to turn the dictionaries into a list of tuples. And then we have this insert statement and we apply it to all the data. So now the data is there and we can verify that by executing a select star request. And then, yeah, let's see what are the first 5 events there. So we see that the data is there. We successfully loaded the data to our data warehouse, to the GitHub events table. And we have these 6 columns there: ID, type, public, created, add, actor ID, and actor login. Cool. So we were able to do this. And before I forget, let us also close the connection. So now the data is there, and we can now start building analytics on top of that. We can start building dashboards, and we can do whatever we want with this data. And even though it works, if we look at this code, there are actually many problems. So first of all, when we specify when we create a table, we hard code all the values, all the fields. So we say that, okay, type is text, public is Boolean. We have to manually do this. And this is problematic if we have, when we want to do more, then we have to maintain a lot of code. So this is not fun to do this. There are other problems, like we don't have automatic retries. We have some code that loads data to our data warehouse. But what if something happens and let's say in a case we don't use DuckDB but use BigQuery. BigQuery is a remote data storage. It's a data warehouse that it does not live on our computer. And if there are network issues and something happens, we cannot insert data, we cannot load data. We don't have any automatic retry mechanisms. Then also there is no incremental loading. So we take all the data we have and we load the entire data set into our data warehouse. But what if we want to run this code tomorrow, right? Tomorrow we will have new events, of course, but also we'll have a lot of old events. We don't want to reprocess all these old events. We want to only process the new ones. So we would solve this problem with incremental loading. And there is a lot of code to maintain. Like if you look at this code, like it's not pleasant, and we need to maintain it. We need to, every time we add something new, we need to also keep track of that. So this is not fun. This is a lot of work. And yeah, we will need a team of engineers to actually maintain this code over time. So these issues are not fun. Let's say we want to address some of these issues. And the use case we'll have is we want to add a new column here. So I'll take the code that we already have for processing events. And let's say we want to add a new field. We want to add a new column, a repo ID, because we want to run this analytics job on multiple repositories, not just data engineering on camp. We also want to do it for our other courses. And we want to know which event belongs to which repository. So for that, we need to know the repo ID. And we right now will add this. So add result repo ID, which is event repo ID. So this way we will copy the repo ID, we will also nest it, and we get the ID of the repo. So the modification here in the process event function is relatively straightforward. Let us also execute it for all the events. So now if I look at process events, we see that there is a new field, repo ID. So now we have the new field in our dictionaries in the processed events. Now we need to load them, to load this particular column back to our data warehouse. And we want to be smarter this time. So instead of hard coding the type information, the schema information, we want to automatically infer it. I will start with, again, opening a connection to our DuckDB. Then the next thing I want to do is I want to understand what kind of columns we already have in this table in GitHub events. So these are the columns we have. And what we want to do now is iterate over all processed events. And if we come across a new column that is not present in this list of columns, in this set of columns, then we create an alter table statement, and then we added this to the set. So this is how we do it. We iterate over all the events we have, and we check the fields, the keys in these dictionaries. And if we see that there is something new, that something we haven't seen before, we try to understand what kind of type of this thing is. In our case, it will be an integer, so the column type will be big int, and we will execute the alter table statement on the GitHub events table, and we will add a new column. So let us execute this code, and we see that we successfully added a new column. Now we need to load the data again, and right now we don't have any new data, but imagine that maybe we do it a few days later. There are some new columns, there are some new events that appeared, there are some events that were before, so we cannot simply just redo the whole thing. So we need to be a bit smart about that. So this is the code we can use for that. So again, first we turn our dictionaries into a list of tuples, and then we construct a SQL query for that. And in the query, when we insert into GitHub events, we do this on conflict. When there is already a record with this ID, we actually update it. So we see, okay, the record is already there, but the field is missing. So let's insert this field. So this is what this query is doing. And now we can execute this query. Okay, this query is executed. And let's actually take a look at what's inside our table now. So now inside the table, we have the same information as we had previously, but there's a new column, repo ID, and the repo ID contains the ID of the repository from which the event is generated. Okay, cool. Now the code is a little bit better, even though it's more difficult to understand now, but it's more generic. So every time we add a new column, we don't need to hard code values. So this code will be able to automatically infer the type of the new column and add this to the table. And so this becomes easier, but as you can imagine, with time, this code will grow and it will become more complex. It will become more difficult to maintain this code. And this is not something that the team will be looking forward to working with, because it will be a big spaghetti, a big file with lots of spaghetti code that is hard to maintain. And even if you will take a lot of time to make this code really good, it's still, you probably don't want to spend time on this library. You want to spend time on innovating, on solving business problems, on creating data pipelines for maybe new dashboards. So you'd rather put your time there than into maintaining this code. And this is why you want to actually delegate this job to a special library that can do this for you. And this library is DLT, and DLT can do automatic schema management. So it handles schema changes for you. Like when you add a new column, it will just automatically add this when you need it. Then it also handles incremental loading. So it ingests only new or updated records. It can work with any destination that you can think of. So here we use DuckDB, but when we switch to DLT, you can ingest data. You can load data into BigQuery, into Snowflake, into Postgres, into anything you can think of. Then it also works better because there is you can ingest data faster with built-in parallelization. And something we also don't have in our code is we don't have transactions. We don't have atomicity. There are no retries. DLT handles all that. So when you switch from your homegrown code for loading data to something like DLT, your life becomes a lot more easier. And this is what we are going to cover in the second part of this course. In the second part of this course, Adrian, my co-instructor, will introduce DLT, which make your life a lot easier. Woo!
So, welcome to Data Engineering for Senior Professionals, the second part of the course, the advanced topics. My name is Adrian, and I'm a data engineer. I got into the data field some 10 years ago. I did 5 years of startups, 5 years of freelancing, building data warehouses and data teams. And then I started working on DLT, or data load tool. It's a dev tool for data engineering that we will learn how to use, which I hope you will enjoy today. So why did we create DLT, data load tool? It's basically coming out of my own need as a data engineer. One of the needs that I had was that it's fast and easy to create pipelines that then self-maintain, and that also the rest of the team can use them or create them, or, So I saw, for example, that data scientists can all do pandas, data frame to SQL. I wanted it to be that easy for everyone to load data in an engineering complete best practice kind of way. So not like pandas to SQL. So this is DLT, the tool that will take your weakly typed JSON data or stuff like that and automatically clean it up and load it strongly typed into a data warehouse or data lake. It basically automates the unpleasant part of the work. So like turning weakly typed data into strongly typed data. It enables the team, and it solves most data engineering problems once and for all. So what I mean is, for example, you might want to parallelize a pipeline at some point. So at DLT, once we added the ability to parallelize, you can parallelize all your DLT pipelines. So it's the boilerplate code that I wish I had. This has already happened. So we created this library, we put it out there, and our early 3K community already built over 20,000 sources. So it's a different dev tool. I would say we mostly care about enabling you and your ability to build with it. You might ask how, because it's a very common question, how do you thrive as an open source project? And the answer to that is that we're an open core company. So we offer DLT OSS for free, no limits, and DLT Plus commercially. What this also means to be an open core company, it means that we aim to make DLT an ingestion standard. Similar companies that do something like this are Confluent, and they create Kafka, or Elastic, who creates Elasticsearch. And in this course, basically, we will learn about how to do data engineering using DLT, because it already has the best method, and how to have, let's say, a happier experience when you're working with your data stacks. So let's look at what we will learn in this session. So first we will learn about extraction. We'll look into different ways to request data from REST APIs. Then we will look at what a DLT resource is, which is basically an extractor, and look how we can configure that. Then we will look at normalization. In the case of DLT, we built DLT to automate this normalization because this is hard and tedious. So you can adjust how that happens, or you can set a data contract, or you can alert schema changes. So we will look into how to do that. After normalizing, we will move on to loading. So we'll look into how to configure write disposition in a resource, understanding how replace write disposition works. It's a step-by-step example. Then we'll go to incremental loading, which is significantly more complex. So we will first look into the theory of how that works, and then we will go with an example. And then we'll look over SQL to SQL copy specifics. So specifically, because the data in SQL is already typed, strongly typed, we can skip the type inference. So we can use arrow or connector X under the hood. I'll show you how to do backfilling, because this is a common question people have, and how to historize data with slowly changing dimension. Then we'll move to performance tuning, which will teach you how to do memory management with DLT so your pipelines never crash running out of memory. How to do asynchronous requesting so you can essentially parallelize extraction, and how to do parallelism on the rest of the pipeline, so for normalization and loading. Then we'll look into loading to data lakes and lakehouses, because there are some specifics around them. So like loading to Parquet files, loading to Iceberg and Athena, talking a little bit about Iceberg partitions and catalogs. Then we will learn about the specifics of loading to data warehouses or MPPs. So understanding how staging works. Staging is essentially like a data lake for data warehouses. And then we'll move to deployment and orchestration with some examples of how to deploy to Crontab, Airflow, or Dagster. Looking forward to guiding you through all of this content. So let's talk about data extraction. We have this notebook here. I'm pip installing DLT with DuckDB. And previously, Alexey was showing you how to do Python imperative API calls. Now I will show you how to do a hybrid type of calls, so something between imperative and declarative, using the REST client from DLT. So the REST client from DLT was actually built for this declarative API client that you can also use. And it offers you some components to make requesting data a little bit easier, because it automatically detects some things, or you can tell it what type of paginator to use, for example. So it's very useful for mixing, let's say, Pythonic code with customizations with just a simple automated REST API client. You can read more about the docs here from this notebook. And you can also self-learn the REST API documentation. You can also find on YouTube some tutorials how to do it. They're quite comprehensive. So I will not teach that here because it would be quite long. So let's do the step-by-step example. So we had the previous example requesting data. So now we will go to documentation and copy a snippet of the REST client, and then work with the other elements and build our request. So just quickly going to documentation. So I'm just going to copy out this snippet from the top. And now let's implement it. First, I will paste it here. We don't need most of these things. So we don't need a session. We don't need a data selector. We need a paginator, but it's not this one. We need authentication. We don't need headers, and we need the base URL. So let's put in the base URL. I can copy it from here. Actually, I have it. This. And let's use also the credential that we were using for the GitHub API, so the access token. We have it in our variable, so let's read it there. So it's a collab user data. Can see it here. Oh, we need to give collab access to it. No, I don't have access to it. And we need to print the data from this paginator. So I'm going to quickly look at the documentation again. Or was it here? So how do I print it? Okay, yeah, this is how I print it. And for us, the endpoint is events. I think it's plural. And we don't have, okay, we need to put in our base URL. And for authentication, we pass our API token. And for the paginator, we actually need to use something called a header paginator. So let's look for the header link paginator, it's called. So just header link paginator, let's copy this. And here, so let's import this one. And here our path was next. And in the documentation for the header link paginator, we also have the variable name here. Unfortunately, it's different. We should probably fix that. But yeah, this is how it looks. Let's see if it works. Then we should get pages of data. User data is not defined. Oh, we need to import the collab user data. Okay, now we basically see pages of data coming, so our example is working. Now let's convert it into a DLT resource. So what is a DLT resource? It's a function that yields data. So we just need to wrap our code in a function and make it yield each page. And then on top of this function, we put a decorator. And what this does is it will allow us to customize our function. So basically customize how it will behave in normalization or loading or all kinds of things. So let's implement that. So let's define a method here. We were calling it paginated getter. So let's do that. And we want to declare that this is a DLT resource. And as you can see, my autosuggest is already suggesting me what to do. Now, DLT, when you yield something, it works with records, but if you yield pages of records, it's also fine with that. It will actually work faster. But DLT will break that page into records anyway. So let's see when we print it. Oh, here. think I need to do something different there, but anyway, now this will work. Let's print it. So as I mentioned, now we have records being emitted, not pages. So as you see, we're doing printing the records. And now you should see basically the same data, but instead of it being like a list of records, it's printing a bunch of records at once instead of printing a list of records at once, right? So it's the same, just slightly different format. All right, in the previous section, we were looking at how to extract data and how to create a resource. Now let's look how to configure secrets for DLT so you don't risk leaking your credentials. So let's try to understand how that works. And basically DLT has configuration or secrets. These are both declarative YAML stores. So secrets is for sensitive data like passwords. This should not get committed to GitHub, for example, while configurations are non-sensitive settings. So for example, maybe which tables you want to copy from a SQL database. This would be okay to commit to GitHub. So there are multiple ways for DLT to get these variables or credentials, and it can either do that through environment variables or from configuration files, or from, so like you do on your local machine, or directly in code. So for example, if you have a credential store, you can pass the outcome of a function from your credential store to DLT. For Airflow, for example, it will read it from Airflow secrets. Anyway, so let's look at how to retrieve secrets from environment variables. So let's set our GitHub access token in the environment and retrieve it via DLT's method. So let's just copy the code we were using before. And just paste it here. And the first thing we're going to do is put this access token into the operating system. So we can do that by using the OS library. So we can just put in the environment variable access token, our access token from our user data. Now it will be available to DLT to read from there. So we should change how we pass this credential here. So we just need to tell DLT that it will get an access token with the name access token from the DLT secrets vault. And then here, where we are passing the API token, we should just pass the access token. So now, as you can see, there is no access token variable here, so it's being read from environment. If everything goes well, let's try it. It did not. And I think we can I think, yeah, sometimes what happens is the Colab session gets a little stuck. So we just need to restart it. So let's try it now. All right, now it worked. If you're not using Colab, this should work every time. If you're using Colab, then Colab notebooks have state, which sometimes can get buggy, and you need to basically restart your session to clear the cache. All right, so we saw how we can pass credentials. Let's move on to normalizing section. So let's talk about data normalization. What is data normalization? Well, data normalization is taking data from whatever shape it's in and putting it into some kind of normal form. Those normal forms could be just some kind of flat form. Of course, you want the data to be typed and clean. So the challenge usually when you call data from an API, you will get some kind of JSON. JSON is an interchange format. It's for exchanging data. It's kind of like a lowest common denominator. It doesn't have types. What this means is, for example, date time in JSON will be represented as string. A Boolean, true or false, will be represented as string. So if you want to be able to work with the data as it actually is, like the types, you would need to type it. So you'd need to convert the string into a date time, for example. Another issue with JSON is that you don't have a clear schema, so you don't know what fields you have. You might need to constantly evolve your schema with whatever comes, because JSON is schemaless. JSON has nested fields. So for example, nested dictionaries, you would want to flatten those into a single level, or you might have nested lists that you might want to break out into separate tables. So DLT will do all of this for you automatically. And what we're going to do right now is showcase how that works and talk about how we can adjust this automatic process. Why use DLT for doing this? Well, this is actually one of the most tedious parts of data engineering. So it's also very error prone. So actually automating it with DLT is, a breath of fresh air. So let's look step by step how that works. So let's look at what kind of data we were loading. It was GitHub events data. As you can see, there are some nested structures. It's mostly nested dictionaries. There might be nested lists as well, but not in this specific event. So instead of manually working with this and flattening it, we can use DLT. And what we do here is we create a DLT pipeline. We give this pipeline a name. We call it GitHub data. We give it a destination. And here we choose DuckDB because DuckDB is an in-memory database, so we don't need to set anything up. We can just spin it up ad hoc as we need it. And then there is a data set that we create in DuckDB, and we call that events. Then we invoke the pipeline object. The pipeline object will take a iterable, so we give it our function. We could also give it a data frame or something like that. We give it a table name to which we want it to load and how it should load the data. So let's just run this code and see what happens. It will tell us it loaded some data. It's running the extractor right now. So now you can see we printed the information of what happened, and it says a load package was loaded. This is basically a Unix timestamp. It identifies a load package. And you can see the tables that were loaded. So we have events payload commits, events payload pull request base repo topics. So basically those were some kind of like nested lists within this event. And here we print the events data frame, so you can see what it looks like. As you can see, the data is clean. And let's print another table. So we have events payload commits here. As you can see, it's unpacked with 2 underscores. This shows you basically that this is coming out of a nested dictionary, and I think this is the nested list. So let's look at the commits. These are commits, basically. So this is a separate table. And we can, as I was saying, join the parent table that we loaded to its children that were unpacked through generated keys. So basically here we have the events DLT ID is the parent ID for the child table commits. So we can run this query and see what happens. As you can see, we have a SQL client here built into the pipeline. This is a universal SQL client. So basically, if you were to load the files, for example, you could still use this SQL client. What we do under the hood is we spin up a DuckDB, and that enables you to query your file system with it. Yeah, so you can see here that we have the result of that query. Yeah, I could have printed it nicer, I guess. But yeah, the query worked. And something quite relevant is a schema was inferred. So I'm just printing it here. You can see what it looks like. Let's look through it. Okay, well, here we go. It's very large, it seems. So let's see what we have in the schema. We have tables, we have DLT version, DLT loads, and events. So these underscore DLT tables are basically metadata that helps DLT keep track of what was loaded. Then we have our events table, and we can see that the integers are integers and stuff like that. Timestamp. Then we have our unpacked columns. We have DLT load ID, which is a timestamp. We have the row ID, which you can use to join, as I was showing you before. Here we have the two underscores, which are basically saying this was a dictionary 4-key in payload. So it got unpacked. You can see the IDs here. Lots of information in there. Okay, I want to get to the end of it because there's some more interesting information. Okay, here we are. So here you see another table, and you can see actually these tables have right disposition. They have some kind of file format if you declare it. Otherwise, it's all default. Some normalizer settings, and here you have more generic settings. So for example, detecting timestamps, what you want for detections to be used. Default hints on columns, you could add more. Normalizers for the column names. So column names, like you saw, they get unpacked, so we need to create new column names. And there's versioning as well. Okay, so now you probably wonder, how can I adjust this normalization? A lot is happening automatically. And like I said, basically one of the parts is you can export the schema, modify its settings, and re-import it. You can also do that from code. And this is a very comprehensive piece of documentation. Let's not get into it now because it's going to take a long time. But you can also just simply reduce the nesting level of tables. So just so you don't unpack data, for example. But in the schema, you can do almost anything from, let's say, changing column types, deciding to remove some columns, and then, for example, setting a data contract to prevent them from appearing again. So you can check on your own how to adjust the normalization. Most people don't need to do that. But you might have some very specific cases. You can also just adjust your data before passing it to DLT, so before emitting it from a resource, to modify it to do whatever is needed. So for example, you could pseudonymize your data before loading it. Okay, now let's talk about data contracts. Data contracts are essentially an agreement between a producer of data and a consumer of data as to the contents of the data. Now, that is a very up in the air definition because fundamentally the producer might be completely outside of your control. The producer might be a browser that is triggering events, and the producer might be somebody that is actually maliciously looking into your website code and sending you some random trash. So it's not an agreement necessarily between the producer but it's an agreement between, let's say, some place that holds the data and another place that holds the data. So for example, when you are doing a data contract that is on event ingestion and the events are coming from the World Wide Web, then the contract is between a piece that checks and the piece that accepts, right? It's about two pieces of software that are talking to each other. So anyway, it could also be that a data contract is an agreement between two individuals, like two departments that are transacting data. But fundamentally, a data contract has two sides of it when it comes to actually validating the data. One of them is validating the schema, and the other one is data quality checks. So validating the schema is called the schema contract. And like I said, we would use that for event ingestion, or basically it's just a technical, let's say, contract or barrier. And data quality checks would be like business rules or data quality rules that the data should validate. So let's look at what we can do with DLT. So because DLT has a schema inference engine, of course, the schema contract is natural. We can easily validate the schema that we read compared to the schema that we already have. So let me just quickly show you what DLT can do in the documentation. It's really to the point. So you have tables, columns, or data types, so it's entities that you can control. And you have the modes: evolve, freeze, discard row, and discard value. Evolve means just the default. It means you don't really have a constraint. Freeze means you have a constraint. So basically, if things don't match your rules, it will break. Discard row means if there is some kind of row that doesn't match the rules from many rows in your dataset, that specific row will be discarded. And discard value basically says if there is a value that is causing the violation. So for example, like we have a new column or something like that, then specifically this value will not be loaded and the rest of the row will. Now let's go to Colab and do an actual implementation. So I have here our pipeline and it has the contract set to evolve completely. So it's like it doesn't have a contract. And I already loaded the data once, I think. I'm just gonna run it to make sure. Okay, so this was the first time it ran, I think, and it basically loaded some data. And this is our data set. And now what I'm going to do is show you how the schema evolution works first. So what I'm gonna do is add some extra data as an integer. And let's see how that column gets added. Of course, when you have a new column, you want to alert it so you can do something about it. So for example, you load a new raw data column and then you want to put this in a report. The analyst should know. So we'll tell you about how to alert it later. But now let's say the type changes from integer to string. Let's see what happens. As you can see, it still worked. And what happened was you got the variant text column. So this is your old column. Because we're loading with right disposition replace, there's all your old data got deleted, but your new data now has this variant column. Now, maybe you don't want this to happen. I probably do, because I want to know when this happens and I want to be able to fix it and merge it later. But maybe the problem needs to be solved at the source, right? Maybe there is a source that you can talk to. So in that case, you would want to set a data contract. So let's say we don't want, let's just load a new column first. Let's set it to freeze. Let's say we don't want new data types. So now everything should work. We should get this new column. Oh, sorry, I wanted to load an integer because now an integer would fit in a string. So let's do it. This. So now it should be fine, but now when I switch it to string, it won't work. So as you can see, it says schema is violated, contract on data type with mode freeze is violated, this column was not allowed. Yeah, so stuff didn't load. Now we could demonstrate the other kinds. I would say, do it on your own fun, and depending on what case exactly you have, you can use any of the modes to prevent schema evolution. Keep in mind when you're playing locally that DLT essentially, like this rejected package, is actually still stored locally by DLT in order to be able to retry it if it should be retried. In this case, it should not be retried. But if you will change something right now, you have a local state that might get mixed up. So you might want to use development mode. You can read about that in our documentation. Anyway, next we'll talk about alerting schema changes. So you know when you have a change that it exists and you can do something about it. Okay, now this is for data contracts, but typically you would just want to receive the data as it is because that is the truth, and decide what you promote to production from the raw layer. So what people typically would do is just load everything with schema evolution into raw data, into a raw staging layer, and then basically apply a schema evolution alert. And let's look at the docs for a second. So you basically have documentation here how to alert schema changes to curate new data. And basically what is happening is in the load info, after we load a pipeline, we have way more information that we can get out. And here we also have a Slack message function that we can use to send this information to a Slack hook, so you get notified. But let's go back to our notebook and see what we could do. So we have this already set up example, but you could just copy this snippet from the docs. And then here we just have our previous pipeline. Slightly different data set, pipeline name, whatever. We can just load this. Let's see what happens. Yeah, I had a different pipeline name here, so you can see, because if we already loaded the data, then the schema is there and it won't evolve it. So we need a fresh one so we can run the code. And then we will see basically what is being emitted here, because we're just printing the column table names. So as you can see, these are all the columns that were added because they were all new, because it was the first load. And you can see basically there's this new column, it has this name, it has this data type, it has this information. It's a lot of data in here. It's kind of crashing my browser a little bit. But yeah, it's a lot of information. My point is that when you have a new column, you could send this alert to Slack and you will know to go into your DBT model or something like that and adjust it to make sure it works. So I hope you enjoyed this section. The next section we will focus deeper on loading and then also talk about incremental loading. So if you need to make a break, you could do that now. See you in the next section. So welcome to the next section, loading. And in this section, we will learn how to configure the right disposition in the resource and understanding how the replace operation actually works under the hood. So first of all, why would we want to do this, configure the right disposition in the resource? And the reason for that is because typically when you have a data source, that data source might have multiple resources, and you might want to configure each of them individually and granularly. And then finally pass them to a pipeline together when you load them. Whereas if you have a data structure like just some records or a data frame, then you don't have a resource and then you can just use the pipeline for the configuration. But you have more options when you configure things on a resource level. So let's look how to do that. So we have the resource here. This is our code from before, and we take the right disposition from the pipeline and we move it to the resource. So that should be it, basically. Let's run the code and see if that worked out. It should load this paginated getter with replace. It did it. Did it here. And now let's look at what actually happened under the hood. So let's discuss how replace works. I'll show you the docs briefly. And here you can see that actually for replace, we have multiple strategies. One of them is the truncate insert. And this is the default one, and it's the fastest. It's also possibly cheaper, depending on the exact technology that we're loading to. It's default because you generally don't need more, but as a shortcoming, it's that there will be no data in the table while we're loading, because what happens is first, if there is a table there, we will truncate it, and then we will insert data. So in the time between truncation and insertion, there will be no data. If you're not fine with this, you can do insert from staging strategy. So this is a little safer because first we create a staging table, and once that staging table is created, so we have the confirmation that everything is working fine, then we truncate the destination table and we move the data over or replace it, depends exactly how it's created, how it's implemented. And finally, we have staging optimized strategy, which is similar to insert from staging, but it has some extra pros and some extra cons. So basically, this is dropping the destination tables in some cases, which means that if you have dependent views on those tables, it will not work. So basically, if you don't have dependent views, you could use it. It has some performance and cost-saving opportunities implemented. Okay, let's go back to our example. So this was what was worth learning about on loading, and now let's move to incremental loading. So let's talk about incremental loading. When we talk about incremental loading, we don't just talk about incremental loading. We specifically talk about incremental extraction, the state of where we are in an incremental load, and the right disposition that we use to load the increment of data. What are these things? So the incremental state is usually a marker or a checkpoint from the last load that tells us where we left off. It might somehow identify the increment of data either by maybe a maximum ID, a last timestamp, or maybe something like the date of the data. Maybe we have multiple rows with like a report date. And we basically save this piece of information so we can use it for the next incremental extract. So once data pipeline has loaded once, we have a state, and we use the state on the next run to incrementally extract data. Finally, we take this incremental extract and we use a specific write disposition to append it to the destination. And I say a specific write disposition because you could replace the data that's non-incremental, you could append it, that's incremental, or you could actually replace a specific increment of data, which could also be incremental despite you using write disposition replace, or you could be merging data or using slowly changing dimension write disposition, which will update the data at the destination. So like I said, we can mix and match to configure different types of incremental loading for different use cases. In our case, we'll do a simple example of how we would load a bunch of events to make sure that we're not loading the same events twice. So we call this incremental loading with a cursor field because of basically cursor field being this event date. And we'll have to follow these steps: identifying the cursor field, using the last value, and then appending the data to the destination. So let's look at the data that we had. This is an example of a record. This is the created at date. And now we need to write our example. So I'm going to take the one we had before. I'm just going to copy this from our previous step and then put it in here. The first thing that I'm going to do is just simply change the right disposition to append, which means that now we won't be replacing the data, but loading it again. Next thing we want is actually to put a cursor field in here. So you can see it's giving me some suggestions already. You can find this in documentation. So this is example, incremental loading with a cursor field. So you could just copy this out. In my case, I will just type it because I have the auto suggest as well. So I'll go with cursor date, and we have the LT sources incremental, created that. This is our cursor field from here. You know, if you had a different field, you'd be using that. We give it an initial value. It's just a default for the first run. What else? And basically what we would be doing right now is also basically we would, so I'm just going to do this. So as I was saying, we would typically need to use the last value from the cursor. In our case, unfortunately, we cannot pass this back to the REST client because, I mean, we can pass it to the client, but the API won't accept it because GitHub Events API doesn't have a way to only request data after a specific timestamp. So what we will do instead is DLT will automatically check, and if it finds any kind of fields that precede this date, it will not load them because it knows they were already loaded. So let's run this pipeline and see what happens. I think I might have a typo somewhere. I don't know. Let's run it and see what happens. Yes. Where is it? We didn't close our parenthesis. So this is our state, and it's telling us how much data was loaded. Because I ran this before, so let's create a new data set, I would say. Because I ran this before, it recognized that the data was already loaded and it didn't load it again. So let's do another data set, events data set 2. Now we'll see it actually loading. As you can see, it actually loaded some data, specifically this much data to these tables. And now let's run it again, and it shouldn't load any new data unless there's some new event. So now it has a state. And now it didn't load it again because it knows it was already loaded. Okay, so that was it for incremental loading in our example. I encourage you to try also other examples, other loading patterns. Next, we will cover SQL to SQL copy specifics. This is going to be a little bit different than extracting data from APIs, so this is why we will cover it separately. Okay, so let's talk about SQL to SQL copy specifics. Transferring data between SQL databases is a little bit different than getting it from an API and loading it to a SQL database, and it's something that data engineers have to do all the time. The main difference is that the SQL database is already structured. It's already normalized. So this means that if we want to get data from there and put it into another database, we don't need to infer schema, we don't need to check types value by value. We just know that, and we can take the whole chunk of data and throw it in, declaring the types in theory. So this would mean that it would be much faster and safer actually to load data this way. So luckily there are a few formats that allow us to read data into this strongly typed format and transfer it like that. So one of them is arrow, like arrow tables. Another one is panda data frames. So let's do one example here, and let's have a look how that works. So SQL source is built into DLT because it's such a common use case. So here we install the DLT PyMySQL, and now we can use the PyMySQL driver. So the source is done through SQL Alchemy, meaning it's actually compatible with most SQL sources. And here, as you can see, we're using a PyArrow backend. This makes things faster. And you can see the data was transferred quite quickly. And this was about 5,000 rows, if I'm not mistaken. So that's very quick compared to an API. You see it's just 1.16 seconds compared to, I don't know, maybe 10 seconds we were taking from the GitHub API. So basically what this does is it just skips normalizing the data. And we can have a look at the documentation to see what else we have for backends. So we have the typical SQL Alchemy backend. It will just yield rows. Then we have PyArrow, which we were using just now. Pandas, you're familiar with data frames for sure. They have types, so this is why we can use them. ConnectorX, it basically completely skips the SQL Alchemy backend. It's very fast, but it's not as configurable as other options. Yeah, and you can find some examples here how to use it. As you can see, basically you declare the backend when you create your SQL source. Okay, going back to the notebook. Let's look at also a benchmark blog post to understand how much different are these backends. And here basically one of our employees did a benchmark and they took DLT with ConnectorX backend. So it's a specific benchmark, it's a specific data set. You can see it's quite large. And this was DLT with ConnectorX backend, very fast, under 5 minutes. This is online tool you can use. This is DLT with SQL Alchemy backend. As you can see, very slow by comparison. There's other tools you can use. And again, this is DLT with Pandas and PyArrow backend. As you can see, much faster than SQL Alchemy. So like Pandas is 3 times faster because we don't deserialize the data anymore. But ConnectorX is still faster than Pandas. So let's talk about backfilling. What is backfilling? Sometimes you have to load a very large table, like an event log, for example, from one SQL database to another. The problem with that is that your infrastructure is probably made for loading daily increments of data. So if you have to load 10 years of data, it will probably be too large for your infrastructure. That would be like 3,000 times larger. So what you can do is chunk your data into more manageable chunks, because if you don't, things can go wrong. For example, your source database might disconnect you after some time. It might time out, or it has a select buffer. When you do select star on a large table, it might fill that buffer and kick you out. Or you might lose connection if it takes a few days, or your runner might run out of time out, or something like that. So many small chunks are much easier to handle. How could we do this with DLT? There is a way that we chunk things, but there are multiple ways, right? You could, for example, chunk your data into time intervals, like days, and then you could load them in parallel. Here, I will show you how you can chunk your data kind of serially. So you can basically load one chunk after the next. So I already have this example put together. We have a SQL database source here from this MySQL database, and we have an incremental load setup, and I set a chunk size of 2000 just so we don't have to run it too many times. There are 4,100 something rows in the source data, so this means that 3 runs should load everything. So we have the chunk size of 2000 rows. We set a limit of 1 chunk, and then we run the pipeline 3 times. Let's see what happens. I'll create here a new data set and we will run the pipeline. And as you can see on the first run, it took 2000 rows, loaded them. Then it took 1999. The reason it does this is because it basically takes one row twice to make sure that there's no, like if you have the same timestamp twice, if you're not taking the interval from both sides, you might miss a row. So in this case, it would rather overlap and remove the overlap than lose a data point. And as you can see on the third run, it only loaded the remaining 170 something rows. Yeah, so that was it. Now let's talk about slowly changing dimension. Slowly changing dimension is actually a type of materialization. It's a loading pattern that we use to essentially version the data that we have. So it's similar to merge or to replace, but we're keeping versions of a record. So I prepared here a small example to help you understand what is happening. So we have 3 records and we have 3 students. And at some point, one of them will get expelled. So we have this data set of students 2 times. We have it the first time around, and then we have the updated version where Draco got expelled. So now when we run this pipeline with merge dispossession and slowly changing dimension strategy, we should get, so we're loading just the first chunk of data. We should get some new columns that are basically telling us, oh yeah, I need to run this. And now I can load my data. And as you can see, we got some new columns. Basically, DLT valid to, valid from. Valid from is basically the time of the load right now, and valid to is the time when this record would get invalidated. So now if we load this expelled version of Draco, what should happen is, for his case, we should have this record being invalidated. Everyone else should stay the same because nothing changed for them. So Draco should get another new record that says expelled, which is valid. So basically this record right now is valid because it doesn't have an expiration date. But it will soon not be like that anymore. So let's run the pipeline the second time around and see what it looks like. So as I was telling you, now this record has become invalid. And we have a new record where the student is expelled that starts from basically the time we just loaded the data. And we have the invalidation date, which is also the same timestamp. So when do we use slowly changing dimension? We typically use this, for example, when we have, let's say, a stateful table like a customers table in source database, and sometimes those customers might change, but we don't have a log of changes, so we need to create it on our side. Why is it called slowly changing dimension? Why not just changing dimension? Well, there's a trick to it. The thing is, if your data changes multiple times between your loads, this means you will not capture all the changes. You will only capture the change from your first extract and from your last extract, which means that if you have fast changes, you will not be able to track them. So the premise of slowly changing dimension expects that the data changes less often than you load it. So for example, it could be that somebody is changing their address. They do that by contacting customer support. Customer support has a long response time. It doesn't happen very often. So then if you capture it once a day, it's enough. But if somebody, for example, I don't know, if it's something like an account statement, which can update a few times a day, this would be the wrong approach. Now, in the next section, we will talk about performance tuning. So stay tuned for that. All right. Let's talk about performance tuning. So my first advice on performance tuning is if it ain't broke, don't fix it. Why I say this is because DLT already has sensible defaults. So if it's working well, don't change it. You might end up breaking it. So let's look at memory management first. What does it do? Well, we use generator for sources, which means that we can request record by record the data from them, buffer it into memory, do something with it, and then let's say write it to disk. The way DLT works is we do this both on extract and on the normalize step. So this means you can actually control the buffer for each of those steps. You can either do it separately or together. So I'll show you here in the documentation how that looks. Basically, this would be like your config file, and you can decide, I want for my source data writer to have this buffer, or I want just for the extraction to have this buffer, or I want just for the normalization to have this buffer, or I want some other source to have this buffer. So you can do pretty much whatever you want there. Why is this important? It's also because when you are writing out the files from the normalizer, this will determine the file chunk size. So what this means is if you want, for example, Parquet files with 100 megabyte file size, you will have to tweak this buffer. So the outputted files have round about the size that you want. And this would essentially enable you to have files of a specific size. This can be beneficial for reading speeds, for example. The default buffer is set moderately low, 5,000 items. Basically, the way you can think about it, if you have a really tiny buffer, it means there's a lot of overhead, so it will be slower. If you have a small buffer or if you have a giant buffer, then the overhead difference is probably not going to be large. So you might as well keep a small buffer. So this is why we have a moderately low one by default. So basically, you might want to just leave it at this. You could increase it. It might go a little bit faster, but it's not really going to make much of a difference. But if you have really tiny infrastructure like IoT sensors, you might want to decrease it. Okay, now let's look at asynchronous requesting. So how does async work? Async is kind of like parallelism, except it's using a single processor thread. So the way you can imagine it is we have HTTP requests, and let's say the work that happens on our side is we make a request that is very fast, and then we wait for the server to answer, we wait for the data to make it over, and this is very slow. So what we could be doing would be to make a request, and then instead of waiting and doing nothing, we could make the second request, we could make the third request, and then when the first request answer comes, we can process that answer. So basically, we don't waste CPU time idling. When should you use async? I would say, well, it's quite easy to leverage with DLT, so I'll show you how to set it. You can do that if you want, but keep in mind that when you're extracting from APIs, you might reach rate limits, so it might not be very helpful, depending on what exactly the API is. But for example, we had a case of a user that was copying a very large Postgres database from one side to the other. And on Postgres, async helps a lot because you have a lot of data that you're transferring and you don't want to waste time waiting for network. So what happened to, I will show you the blog. So what happened in this case, this was yami.eu. Basically, what's the business model called? Basically they have to copy a very large database. And what happened to them was most SaaS vendors have defaults that will cost you more money, of course, they're incentivized to do so. So what happened to them was they were copying data on like 15-minute syncs, CDC with 5-tran, and that's quite expensive. But due to 5-trans practices, what happened was they added a log table that was very large, and by default, 5-tran will decide to automatically start copying this in full load on every run. So if they have a sync happening every 15 minutes, this means this giant table gets synchronized fully every 15 minutes. So that's extremely expensive. And that's what happened to them. And basically, they decided to stop working with Fivetran at that point. And Martin, their CTO, looked for open source solutions, and he went for Model Labs, which offers you serverless compute and DLT. He did async, and he was able to achieve 10 times faster transfer speed by transferring his whole database, and almost 200 times cheaper by using DLT on model serverless. So that's why you should use async. Basically, when you have very large extractions that you need to happen very fast, so lots of throughput. Now, how to set it? I'll show you in documentation. It's actually very easy. So if you know how to use async in Python, you can just define an async function as a resource. If you don't know how to do it, you can just define a normal function and say parallelize true in the resource, and then it will just work that way. Okay, so now let's talk about parallelism. When should you use parallelism and how to set it? Well, parallelism, first of all, you have a default, and you can have parallelism on extract, normalize, and load. And oftentimes the extract and load are bottlenecked, so increasing parallelism there won't necessarily make things better. So it depends on the technologies, on the source and the destination. And increasing parallelism on normalization would actually help a lot, typically, if you're doing it, because that's actually the compute heavy part. So let's look at some benchmarks. So here is SQL Alchemy benchmark, and here we have the default, which is 5 workers. And this is why I was telling you, if it ain't broke, don't fix it. So total time here is 37 minutes. You could optimize it, but if you could also make it much worse. So I would say, unless you're really looking for something specific, just leave it. And you can see here that the parallelization makes a big difference on transform step. It also makes a significant difference on load, but not on extract in this case. And for connector X backend, because here we don't actually have any transformation, what is happening is the transform time is actually increasing when we increase workers. This seems paradoxical, but because we're not actually doing any transformation here, then what we see is purely the overhead time. So because we have more workers, we have more chunking, and this causes basically more overhead. We have a little more. So how do you set parallelism with the pipeline? So you can set it on extract in the resource. For normalization and loading, you can basically declare the workers in your config, as you can see here. So it's very easy to leverage. You can definitely just see what works for you. Okay, so we're done with the performance tuning section, and next we'll talk about loading to data lakes and lakehouses. So let's talk about loading to data lakes, lakehouses, and catalogs. Data lakes are a collection of files in online storage like S3 buckets. And we call such destinations file system because, well, they act like a file system. You can create files, you can read files, you can delete files. And DLT supports a local file system and all major storage bucket providers. We recommend that when you load data to a data lake, you store it in Parquet format, which is a strongly structured format. In some cases, you can register the loaded data also in a catalog afterwards, for example, AWS Glue. This enables you to query it with available compute engines. And for table formats, DLT supports Iceberg and Delta. Catalog is optional. So why would you use data lakes and lakehouses? Well, a data lake, you would use it for 2 reasons. Either you need to store unstructured data, or you have some kind of like weekly typed data and you want to structure it later. For data warehouses, they only store structured tables that can be modified. So this is very specific use cases. We usually use them for reporting, analysis. And finally, lakehouses are kind of for both use cases, so they provide both unstructured file storage, but also a way to treat files like tables. So let's do a step-by-step and load Parquet to local file system. So local file system is just your local hard drive. So let's follow this example. So step 1, you'd set up a local bucket or a cloud directory for storing files. In our case, we just need a local folder. Let's call it content. This will happen on this notebook. We'll take a look at that soon. And then we need to define the data source. We've already done that somewhere. Oh, it's here. Then we need to change destination to local file system, because before we were loading to DuckDB. And finally, run the pipeline. So we've changed the destination already to file system. We've set our bucket URL, and now let's run everything. Okay, you can see that some data was loaded. We can take a look at data. Okay. Here it is. You see fs data, events. Yeah, so this is the Parquet file. We can list it. As you can see, it's the one that just got loaded. And we can look at the contents of this Parquet file. As you can see, we can access it as a data frame. We could also query it using the SQL client, which will then spin up a DuckDB in memory, so you can run your queries. Okay, let's take another example. Let's basically move from Parquet to local file system to Iceberg on AWS S3. So in this part, we will learn 2 new things: switching from local to online storage bucket destination, and switching from Parquet file format to Iceberg table format. So switching from local to S3 storage, first you need to create a bucket. I've already done that. Then you create AWS credentials. I've already done that, and I've placed them in my secrets. Then you need to set the S3 bucket URL. I'm doing that over here. And then you need to modify destination settings in your pipeline, so it's actually like Iceberg. So let's do that. Install the necessary dependencies. Then we're basically putting our access keys into destination file system AWS. We declared the region name. I'm not sure if we need it for file system. We do for Athena. Okay, for bucket URL, we basically have this bucket. And then we choose destination file system because we're loading again to file system. I have a different dataset name, file system S3 Iceberg data. And we changed from loader file format, so from Parquet, to table format, which is Iceberg. We could also switch to Delta. But anyway, we have Iceberg right now, so let's run that. Okay, so that seems to have worked just fine. Let's take a look in our bucket. Okay, so this just got copied here. As you can see, I don't see my timestamp. Anyway, it's just now. And you can see, for example, your events data. This is the Iceberg, basically, metadata. Okay, now let's talk about loading to AWS Blue catalog. So what does loading to a catalog actually mean? So it means taking your weekly typed source data, your JSON, and then typically you might want to clean that up, because when you put data in a catalog, it's kind of like a database. So you want flat, clean tables that are typed. So you don't want to put raw data in there. So by using DLT, you can just put basically your strongly typed data directly in the bucket, and make it available to the catalog. So just register the tables. If you're not using DLT, then you need to do something else to clean the data in the meantime. And then you could access it. So, as I was saying, to copy data to a catalog means to copy it to file system storage and then tell the catalog where the data is available. And the way you'd configure it is just as before. So you'd have your local bucket URL, but now you also have a second destination. So now first we have a destination file system, but now we also have a destination Athena. And this is how we configure our pipeline to use these two destinations at the same time. We basically say that our final destination is Athena and our staging is file system. I'll get into what we mean by staging a little bit later. Right now, just consider that this is where your data is stored, because the catalog doesn't actually hold the data. It only holds a reference to the data. Now let's look how we could partition our iceberg tables, because partitioning is relevant, especially for reading performance. So Delta tables use Hive style partitioning, so you just use an existing column, while Iceberg uses hidden partitioning, so you could use an existing column or something else. So a simple Delta example, you could just, in the resource declaration, say that you have table format and what columns should be used for partition. For Iceberg, it's a bit different, because for Iceberg, you can essentially, you can use something else for partition than existing data columns. So you could pass a bunch of columns, or you could create a partition on month. I'll create that. And then this would be used as a partition date. So this is kind of like a calculated partition. This is in a way better because it allows you to, let's say, if something changes in your source data, you can update your definition here. So you still have your partition field, including the new reality of the data. So basically you don't have to migrate tables. Once you set a partition, you cannot change it though. Okay, so now that you understand how you can leverage Iceberg, Delta, or various things on data lakes or data lakehouses, let's move over to loading to data warehouses and MPPs. Now let's talk about loading to data warehouses or MPPs, also known as massive parallel processing databases. So differently from data lakes or lakehouses, data warehouses are most like a traditional database. And they are services that use multiple machines in a cluster to get the work done at a large scale. So they shine at columnar operations, like aggregations, which are typical operations in a serving or analytics layer. However, due to their columnar storage, they are not optimal for lateral operations like the T in ETL. But due to their accessibility and scale, they are widely used as a compute engine for transformations. So one of the things you need to understand about these databases is that they usually have a leader node that interprets SQL and communicates a plan downstream to a number of compute nodes. And there is a slow way of loading data for it and a fast way of loading data. So the slow way of loading data would be to pass the data to the leader node. And now we have a single node that can process this data. And if we pass it in SQL format, it's going to be particularly slow because it needs to convert it. So the fast way would be to, instead of passing SQL data to the leader node, that we pass entire clean data directly to the compute nodes, and we tell them where, or rather we tell them where to get it, and they take it themselves. So basically, this is called staging. You stage your data to an online destination, and then you tell the data warehouse where this data is and what format it's in. Then the data warehouse will tell the compute nodes to go and read this data, and they will do this in parallel, which will be much faster. So the staging layer is handled differently from one vendor to the next, and here I will just compare BigQuery and Redshift. So for BigQuery, we can stage data on our local machine or on a bucket, but for Redshift, we're only allowed to stage data in a bucket. If we want to load data to Redshift without staging it, we can still do an insert statement. It's just much slower. So I was saying it's typically a storage destination, and here are some examples of how you would configure it. So as you can see, just like when we were loading to a data catalog, essentially here it's the same thing. We're putting, well, we're putting data in an external place, and then we're telling the database that it can read it from here. Differently from catalogs is that now the database will actually read the data into the database and convert it into its proprietary file format, which might be faster. But there are also hybrid modes. So for example, you could have external tables, which are essentially something like Iceberg on storage, and you make it available in BigQuery. And what this does is essentially turns BigQuery into something more like a catalog. So it gives you a way to package compute and to access the table data, but it doesn't actually store the data. Similarly, you have external staging, like I was telling you about BigQuery, that basically enables you to put your data to be loaded locally, and then somehow this ends up being read into the BigQuery storage without going through the leader node. So let's run this example. I prepared it here. First, let's install requirements. I've already put my credentials in here. So BigQuery destination credentials. Let's just run our function to be sure that we have the data. And now I'm setting destination BigQuery credentials, which is just my service JSON, into environment. And I'm running the pipeline on BigQuery. And then we can have a look in BigQuery. Okay, data got loaded. I'm not sure if I haven't already loaded this data because I was looking at it earlier. So here I am in BigQuery, and you can see some data here. So you can see the data preview. As you can see, this is what it looks like in our database. And you have also the child tables that you could join. We also have some different tables here. So DLT stores metadata, like this is the incremental state. And this is tracking what data was loaded. And I think this is for the schema version. Yeah, so you can also load actually the information that you get after running a pipeline to get even more metadata if you want. Okay, so now that we loaded our data to BigQuery, you can use it there. For example, what remains for us is to take a look at how we can deploy our pipelines. So let's look at some deployment and orchestration options. Okay, let's talk about deploying a pipeline. And first, you need an environment to deploy it to. So if you don't have one of the easiest to get is just GitHub Actions. If you are using GitHub, you can just use GitHub Actions. It's a serverless compute environment that you can spin up as you need. Why should you use GitHub Actions? Well, because it's serverless, it means it's going to be very cheap. So instead of renting the machine and deploying there, you could put it on GitHub Actions, and it will probably be like 10 to 100 times cheaper, just because it's serverless. Why you shouldn't go for GitHub Actions is because it's not really made for data engineering. It's made for CI runs. So this being said, you can run Python scripts on it, but it will not be, let's say, comprehensive for data engineering. So you will not have easy chaining of things like loading, and then, I don't know, other actions like transformations, or your schedule will not be accurate. So for example, GitHub Actions when you set a schedule, it may or may not follow that schedule. So it might actually start your pipeline like half an hour later. What this means is that if you're deploying it to run in the night, it's perfectly fine. But if you have some more strict engineering requirements, GitHub Actions won't do. So let's look how we can deploy to GitHub Actions. It's quite straightforward. So the first thing that I will do is I'll create a repository. I'm just creating an empty repository. And now I will create a code space on it. Takes a minute, but it's generally pretty fast. Okay, so we have our README in here. Let's make a plan. First install DRT, then init an existing pipeline, because we just want to demonstrate deployment now, not writing pipeline. Deploy to Git Actions, and finally run. Okay, so first let's install DLT. Make my screen a little bigger. We install the library. After that, I think, yeah, I will need to install DuckDB and CLI. I want to load to DuckDB because I just want to demonstrate this and not set up credentials. And I will also need the CLI because we will do some commands here. Now I will init the GitHub pipeline. DuckDB. So the command is dld init source name, destination name, and to create some files, scaffolding. It will basically grab the verified source for GitHub and give it to us here. So let's look at the pipeline. Pipeline has a bunch of pipelines actually. We only really need one, so let's comment out the other ones. Since there are multiple pipelines here, DLT will ask us about them later. So now that we have the pipeline, let's run it once. To do that, I need to set up my secrets. So remember this access token. Let me copy that in. This is a read-only access token that I will invalidate afterwards. So don't show your access tokens to people in public. This one is okay. And now that we have the access token, let's run the pipeline. It's called the GitHub pipeline. Now I'm running the pipeline because once DLT runs the pipeline, it scans everything and it creates a trace. Like you remember, we were expecting this trace. And this will enable it to do the deployment. So now that we've done this, let's do the deployment command. And I will double check the docs because I don't deploy every day. And I don't remember off the top of my head. So we install GitHub CLI. This is a deployment command. So DLT deploy pipeline name, where, and then the schedule. So let's copy this in and adjust it to our pipeline. Okay, so it's asking me if I want to paste, and let me fix the pipeline now. It's GitHub pipeline and schedule. This means in cron language every 30 minutes. We have some dev mode here. This wouldn't work in production, so this is why it's asking us now, do you want to change it? I don't want to change it. It goes to DuckDB, it doesn't matter. It's going to do this for all the pipelines that have it. Now it's asking me which ones do I want. Reactions or something else. I want reactions. With this thing, okay. Okay, now it gives us instructions of what to do. So it's telling us go to this URL and put in your access token. So I will do that now. Okay, I went to this place and I have repository secrets here, and I will just paste what it gave me. Okay. And now we need to push. Where is up here? Okay, so now I'm back in our window and it says add the files, commit the files, push the files, and then it should be done. Okay, so let's, oops. So I have a command for this. So I don't wanna, okay. I want to add everything and not just if here we go, git add, git commit, everything, commit message. Now we push it. I will show you how we run it now. So we'll go to GitHub Actions in a second, just on double check. And here we have the workflow that we deployed, and we can run it, or we could wait. It should trigger it every 30 minutes. Let's not wait. Okay, so now it should queue up this workflow, and this workflow has two tasks. One of them checks if the pipeline is already running, because we don't want any collisions. And it's not, so it will start the pipeline. Or I can go in here and see what happens. So as you can see, it set up an environment. It's installing the requirements. And after it installs the requirements, it should just run the pipeline. I think that might take a few seconds, maybe up to a minute. Okay, we can also just come back to it later and see what happens. It takes too long. Finally, it's running it. And that was it. Something. It finished it very quickly. As you can see, it loaded some data to the local database, and that was it. Yeah, this is a summary of what it looks like. You can see multiple workflows or multiple runs would show up here. Okay, next we'll look at another way of deployment. Okay, let's talk about deployment to Crontab. Why am I smiling? I'm smiling because it brings back memories. So specifically, orchestrators are actually more of a last decade kind of thing, at least for data. I would say 10 years ago, we didn't have good solutions in orchestration. Maybe some of you know Jenkins, but essentially the pattern was that you'd just schedule a Crontab script, and that script would be generally some kind of entry point in which you'd have some kind of, let's say, dependent logic where you'd manage your dependencies, where you'd have, let's say, multiple entry points if you have different schedules. But essentially, it's just a text file that you manage. And let's talk a little bit about it, how it works. So cron is actually the utility, like the application that is running in the background and checks if conditions are met to run a task. So imagine it kind of like a scheduler from Airflow. Crontab is just a cron table, and that is basically a file with your scheduled jobs. The way you would schedule a job is basically open up your Crontab file. So just each user has one, other users have a different one. You can also have like a super user Crontab. And essentially what a Crontab is, it's a schedule in this format, and then the command to execute. And here's, I just copied this from GPT because it gave me a nice explanation. And typically this is just like a shell script, and you might have more of your script here. So for example, it could be that you're logging, or it could be that, I don't know, you're doing something else. But yeah, this is basically how the schedule works. The first thing from the end is the day of the week, day, month, day of the month, hour, and the minute. So basically with this syntax, we can generate almost any pattern. You also have some special keywords. You might recognize them from scheduling and other things as well. But yeah, there is an equivalent you can just use. As I was telling you, you might want to log what is happening, because these scripts are running on a server somewhere at night, and if you don't log, you don't know what happened. So you want to create a log file. If you work with multiple people on the same machine and scheduling things together, like maybe you're a couple of people and you're using the same cron tab, maybe you should use the sudo cron tab. If you do that, you need to pay attention to your variables and permissions, because essentially the sudo cron tab will have permissions to almost everything, but it won't have your environment variables, whereas your cron tab will have your environment variables, but not access to everything. So just make sure that, you know, when you schedule it, maybe test it to make sure if it runs. So a normal pattern would be, you know, that you create your jobs and then you set your schedule to run in the following 5 minutes or something like that. And then you come back later and see what happened. So when it actually goes out in the night, you have some certainty that it will run. This is not the nicest workflow, but it works. So what I will do next is demonstrate how to do it on VM. So basically I'm on a cloud, Google Cloud, and I created a VM just for this. I already installed Crontab on it, but I will run through it once more anyway. So what I will do is just SSH into it, and I will present you from here once it is loaded. Okay, so it's been a while since I used Crontab. I mentioned this because things are not going smoothly. So what I did was I got this machine, and the first thing I did was I checked if I have Crontab installed, and I do not. Why not? Because Google machines, Google Cloud has something called Google Cloud Scheduler, which is a scheduling service for scheduling Google Cloud services. Now, it's great for scheduling Google Cloud services, but it's not a Crontab replacement. It doesn't do the same thing. So it's functionally a replacement. Here we want to teach Crontab. So I installed Crontab. I created a Python file with a DLT script inside of it, and I tried to run it. Now, let's see how far I got. This is what I have, so this much you could do as well. Just copy a Python file with DLT inside. Here I have a log file because I tried logging, I tried running in my Crontab. So let me show you what I have so far. Crontab -L to list. And you can see I have already scheduled for 9 in the morning with Python 3, this script, to log into this log. Now, let me quickly show you this script. So you can see it's just like producing some random stuff and loading it to DuckDB. Now let me show you the Crontab. Crontab -E to edit it. And here I could edit it, but as you can see, all I have this line, so I'm gonna exit and show you what's in the log. So let's do nano log file. And as you can see, something is not going well. I scheduled this a few days ago when I was trying it out, and I didn't realize that there's a problem, but module not found DLT. So okay, let's install DLT. Exit. And the computer says no. It says if I want to install this package, I can do it this way. I've already tried this way. It didn't work. So if you want, because it's a Debian package, so if you want a non-Debian package, you have to do a venv. So let's do a venv. I haven't done this before, so let's hope things work out. So let's just do Python 3. Let's creating a venv. Okay, now let's try installing DLT, and this works. And now let's try to run our script x.py. Okay, fine. I need to install DuckDB. If you're using Z shell, you'll have to quote square brackets. Okay, now that we have it, we need to adjust our cron tab because so this is our entire venv path, and this is basically where Python is. So what we need to do is in our cron tab, we need to replace our Python 3 location with this. So we have usr bin Python. This is not good. We need to change to venv bin Python. So this looks good, I think. Okay, and it's taking the script. Yeah, let's see. I messed up. Okay, it's saved. Now I will exit. I will confirm that I saved it correctly. So yes, it looks fine. Now I will actually run this command. Let's do deactivate, and now let's try to run it like this. Okay. Now let's do nano log files to see if we have anything new in there. And yes, we have new. As you can see, the last run actually worked. Cool. So that was it. Yeah, so, if you want to try Crontab, I hope this makes it easy for you and you understand everything you need to do about it. As you can see, there are some gotchas about your credentials, your environment variables, your permissions, and so on. But it's nothing that you can't quickly get through in a few minutes. So stay tuned for the next sections about advanced orchestrators. All right, so let's talk about Dagster. What's Dagster? It's another orchestrator. We were previously talking about GitHub Actions and deploying to cron. If you're not one of those people that worked with really old stuff, then probably Dagster is for you. So what I mean is, 10 years ago, we used to deploy stuff on cron tabs. 8 years ago, we used to go to Airflow. Now that was 8 years ago. That's a long time ago. People change, attention spans change, and we have a new generation of developers. And if you haven't worked with Airflow yet, then Dagster actually has something new to offer besides a basic orchestrator, and that is asset lineage. So an asset in Dagster is essentially a data set. It could be a table, it could be a CSV file. And basically this concept enables you to, let's say, focus on the actual data set and understand what is happening to that data set, understand the relations between data sets instead of focusing on task. The problem with focusing on task is that tasks do not represent data sets. They might represent multiple data sets. So you might, for example, load 5 data sets, then transform 3 of them, then I don't know. And the problem is that, and then, you have a separate DAG to transform the 4th. And the problem is that with that is that you don't really understand how they relate anymore, especially when these things are running across different orchestrators. Now, Dagster is able to actually wrap Airflow to kind of have everything under one central command plane. So yeah, our team actually likes Dagster because it's easier to work with generally. Myself, since I've used lots of orchestrators, I don't use orchestrators that much. I try to do mostly just local development and just have the orchestrator as a final logic layer. Yeah, everyone has their different workflows. So just see what you like best. Like I said, our team likes Dagster. So I'll just put on my Dagster cap and do the demo of how to get the DLT pipeline on there. So let me share my screen. Okay, so I have here my PyCharm with the repo that I use to deploy to GitHub Actions. So I'm just going to create a new folder here. I was in a non-existing folder. I cannot go there. Funny. Okay, so now I'm in the example folder, and I will create a Dagster folder. And go inside of it. Okay, now I will look at my command cheat sheet. It's very easy to get started with Dagster, and what I really like about it is how easy it is to set up locally. So first I will pip install it. I've already pip installed it, but just for the sake of demonstration, pip install Dagster embedded ELT. So just this one has DLT inside. So let's just do that. Okay, and our next command. Okay, let's hope everything is fine. So let's confirm we are in the right folder. And now let's create a Dagster project scaffold. We call it GitHub events because we want to deploy our GitHub events pipeline. And let's see what happened. So we have some project scaffold created here. As you can see, this kind of looks like a Python project that you can pip install. So now I'm going to put my code in. So I create a new file. I call it GitHub resources. I paste my code in here, and as you can see, what's special about this code? Oh, I don't want to load to storage. I want to load to DuckDB, so I'll get rid of this part. So there's something new here, and that is a DLT source. A DLT source is just a container for resources that allows us to package them together and pass arguments together, for example, or reuse some arguments or code. So here a GitHub source is just returning our resource that we have here. And it's needed by Dagster because Dagster will wrap our source in its asset definition, which is needed to deploy it. Okay, now that we have our code, let's we need to adjust our assets. So paste in my code. So what does this do? So first of all, this wraps the pipeline. The pipeline runs the GitHub events. And here we want DuckDB. Okay, this looks fine. And now we need to go to definitions and add our definition. Or asset definition. So as you can see, this is all we're doing. We're just grabbing everything DLT. Okay. Now what we're going to do is, remember I was telling you it looks like a Python project? Well, that's because it is a Python project. So we're going to go inside of it. And now we run this command. Oops, not this one. So we installed this local package named dev. This will allow us to run it with Dagster. Okay. Now let's run it with Dagster dev. Fingers crossed. Because of this conflicts, I don't want to solve them now. And these conflicts appeared after I recorded Airflow on video. Since I'm reusing the environment. Okay, it says it started it up. I don't see any errors immediately. Okay, so it looks fine. Let me share the Dagster screen. So basically our asset got deployed and we can run it if we want. And yeah, now we have our run queued. If the code runs successfully or not, depends on if I made a mistake or not. If I put in all the credentials and everything, it looks like it's working fine. Okay, I will switch back. Logs are coming out. So yeah, this is it basically for the Dagster. Very easy to just try it out, so I encourage you to. If you are really nice to them, they might also offer you a cap. So, just book a demo with them and drop them a hint, who knows. Next, we will talk about Airflow. All right, let's talk about Airflow. What should you know about Airflow? First of all, let's talk about what is it, when should you use it, a little bit of history of how it came to be. Then we'll do a demo and see how we can run it, deploy to it. So first of all, what is Airflow? It's an orchestrator. 10, 12 years ago, we didn't really have orchestrators. And we were basically just putting Python scripts or Bash scripts in the Crontab and saying what should happen in there, like run this first, run this next. And that's how we were running our jobs. Now we have orchestrators that let you, let's say, create workflows that say how the tasks should run one after the other. And Airflow is probably one of the first ones that actually was kind of functional. So 8 years ago, I believe, I was working on a freelancing project, and that was the first time I encountered Airflow. The task that I had to do was essentially a disaster recovery. So like lots of things happened throughout the years and they had to be consolidated in some clean form. And basically what we were doing, we were comparing Airflow with other orchestrators like Azkaban. And the nice thing to understand is that a workflow file, like a DAG file from Airflow, is equivalent between orchestrators because it's basically just some logic about take this task, run it, then do this thing next, maybe transfer some information. So that being said, if you start with Airflow and you don't like it, you can always migrate away. Why should you use Airflow? Well, the first reason is because everyone is using Airflow and you should understand how that works so you can work with everyone else. Well, really not everyone is using Airflow. But essentially Airflow is kind of like a standard. You will find it a lot. It's very easy to scale if you are using a hosted version. And what I mean here is we're actually using Cloud Composer from Google Cloud when we want to use Airflow. And that is because the Cloud Composer hosted version has all kinds of things like scaling, CI/CD, so it's just better. You don't need to manage it yourself anymore. You can also use hosted versions on AWS. I've heard it's not as good. I haven't used it myself. You can also just self-host it if you want. And I believe that there might be multiple businesses offering hosted versions. So who should use Airflow? I would say if you're a senior person that has used Airflow before, I don't need to explain to you what about it, why you should use it. If you're a junior person, maybe try using Dagster first because that's a different paradigm. So if you can understand that first, I would say then Airflow is going to be easier kind of afterwards to understand what is happening there. And also you'll understand what happened in the last 10 years of software development and kind of like what you'd be missing if you go for Airflow. Now, that being said, let's take a look at how we can run Airflow locally and deploy to Airflow locally. So I will show you the documentation that I'm looking at. So I'm just going to follow this quick start from Airflow. So basically I will set an Airflow home folder. And this is where Airflow will create all kinds of files. So you can do it in like some generic folder or in project folder. I will do it in my project folder because this allows me to easily, it's self-contained. I can just delete it if I don't want it anymore. Then I will use this to install Airflow. There's more information here. It will basically get the right version for your computer. And then I can run it with Airflow standalone. I'll do a few more configurations in the meantime. So let's switch to my PyCharm. Okay. So I actually already have here an Airflow project that I was presenting earlier. And I will just reset it. So what I mean is I will go up one level, and now I will delete this. Okay, so now let me make a Airflow folder. And now we go in there. Now I will make an Airflow home folder because I want that to be separate. And now let's do this Airflow home export. So I will run this command to export Airflow home variable with this value. Okay, now I will run the Airflow installation. So just copy pasting this block. I've already installed it actually, so this will go very fast. Okay, so now it's installed. And what we need to do is see if we can start it. Oops. And if it works, it should create some scaffolding now. Yes. So it's creating databases, roles, all that kind of stuff. It will create a user for us and give us the credential. See, here it is. I'll just paste it in here because we will need it later. In case you miss it, it's also shared here. So you see this was created automatically. And we have our password here. So now I will close this. I mean Airflow. Okay, so we're here. Let's create and let's create the pipelines folder. Stack created. Okay. And now let's create our Python script. Let's call it GitHub resources.py. And I will copy out the code that I was using before. DuckDB, I need to get my resource that I had before. I'm using the one from the Dagster example, so just let's do this. This is twice. Okay, so what I have here is just our resource, and as you saw before, we're wrapping it in a source, just like Dagster. And we have a DuckDB pipeline, and now let's try to run this. Okay, so we loaded some data, and now we need to create a scaffold for the deployment. So we need to install the DLT CLI. I already have it, but I'm just going to do it anyway. And now I will do the DLT deployment command. DLT deploy GitHub source. Now it's called GitHub resources. To Airflow Composer. Okay. Now let's create a DAGs folder in our repository. So it will always create it, I think, on the top level. Yeah. So, it's because this is how you typically set up your Airflow repo. I'm just going to copy my pipeline in here because it's too, I don't even know how to import it from there. Okay, and now in our DAG code, we have this from GitHub resources, import GitHub source, a source. And now this will import our source in here, and DLT should know how to unpack it. Here's our destination, DuckDB. So when we do the deploy command to create the scaffold, DLT uses the last run trace. So we must have run this pipeline before it can actually do the scaffold. So this is why we had the DuckDB in there, but for destination, but here we could have something else, right? So you could just run it locally on DuckDB and then in production deploy it to BigQuery or Snowflake or whatever. Yeah, so this is why we have it here. If we had more resources, we would essentially DLT can create a DAG inside. So when you say pipeline run, you might have dependent resources. To give you an example of a dependent resource, it could be that we're requesting user IDs from one API endpoint like users list. And then we use this list to do two things. One is we request their orders, and the other is we request their details. So in order to not request the user list twice, once for every resource, we actually can declare that the resources are dependent on each other, and then the information from the list resource will be stored so both the other two resources can use it. This would create a DAG inside, and this DAG can then be unpacked into Airflow. Now let's see what happens if we run our Airflow standalone now. It should basically see these DAGs. Oh no, it won't, because I did not declare our home folder. Let me see. No, I'm sorry. I mean our core DAGs folder. So we need to declare where that is, and it's here. Because if we declare the wrong thing, it cannot see our DAGs. Okay, now we need to start Airflow. And I will use this login. I will switch now my screen to the local host. And this is Airflow on localhost now. And it doesn't see any DAGs. It has to. So it said that the scheduler was not running. Now basically Airflow will check what DAGs are there and start loading them up. Okay, so it just sees this one. This is fine. Let's open it. Let's look at the graph. So yeah, it's just one task, but essentially if you had multiple, this would be like a complete DAG, and you can run it if you want. And you can see it in PyCharm as well that it's running. But yeah, now basically Airflow will start running this. And of course, it takes a while. If you were not running locally, but you had to deploy to Cloud Composer, you would also have to add credentials here. So like in variables, we don't have to do that for local. And you'd also have to add Python DLT to your requirements when you are creating the instance. So you have it there. And yeah, you can see here, the run was successful. Yeah, you can see the logs here. Yeah, that was it. So yeah, thank you for watching the Airflow part. Hey folks, so we have one more chapter, and that's how do we generate pipelines using LLMs. And it's totally possible, and we can do a lot, and it's not going to replace data engineers anytime soon, so don't worry about your job. Rather, focus on how you can leverage it to build faster. So first, let's try to understand the problem. Why haven't we created so far a pipeline generator that just magically creates your pipelines? And the answer to that question is because it's really hard. It's actually a really hard problem. And this is also why your job is safe, at least for now. Specifically, let's look at the actual problem of building data pipelines. And this problem is, let's say, building it. If you have all the information, that's an easy problem. And then there's the hard problem of actually getting the information that you need. And to build a good data pipeline, you need two types of information. One of it is the kind of info you will find in documentation. And that is like pagination, endpoints, authentication. And then there's the kind of information that you need that you won't find in documentation. And that is, for example, that how do you increment an endpoint? How do you load this efficiently? Or how do you, let's say, request a detail endpoint that actually needs an ID from another endpoint? Stuff like this might not be explicit in documentation. So this is where, let's say, a little bit of guesswork, a little bit of domain knowledge, trial, and understanding come into play to create a really good pipeline. And I think if we are to approach this problem from a purely one-shot LLM building everything, it's not easy to solve. But if we take what the LLM did and just put on the final touches, and if we really understand how it works, then we could potentially make it much easier to take over what the LLM did and finish it to basically have a really good pipeline really quickly. So this was kind of the problem definition. I will tell you now briefly one experiment that we did before. So one way to approach this problem would be with LLMs, but when we experimented like 1 year ago, LLMs were not ready for this. So we thought, okay, well, if you need to fish out 10 pieces of information from documentation, you're going to have a bad time because errors will compound. So what we did was we tried to do a deterministic LLM-free approach. We took an open API spec, which is essentially all the information that the documentation would be generated from. And we extracted the relevant features, like the information that is present in the documentation, and we tried to guess the rest. And the results were reasonable. Basically, whenever the open API spec contained quite a bit of information, as long as the API was not completely innovative, then this worked quite well. Now let's look at the LLM first approach and how we can do it. I will show you next how we can work to create, let's say, prompts for the LLMs to do this work for us. All right, let's look at how we can turn this theory into something applied. And I have here a Notion page, and I'm going to walk you through it. So first, let's talk about separation of concerns. We have extraction, we just talked about that. Construction, we talked about that too. And memory, we didn't talk about that, so let's discuss it briefly. Why do we care about memory? Because memory will be the source of hallucination. So if your LLM doesn't have access to documentation, you could ask it, hey, build me a pipeline for this source and see what happens. It might completely hallucinate, or it might do something sensible. Chances are, if you use a common API like GitHub, it will know what it's about and it can do reasonable pipelines because all this information is out there in many places. But if you use something obscure, results will be purely hallucinated, which might be fine if the API is following most common patterns, but it probably won't be. So let's look at how we can, first of all, generate an LLM-friendly documentation to turn our REST API docs into something that LLMs are really good at leveraging to be able to build with it. So I want to combine our REST API documentation, this REST API source with the advanced configuration into an LLM-friendly doc. So I will just take everything from here and give it a prompt to please do that from our documentation. So I'm telling it make sure it's rich with the examples. Anyway, it knows what to do. I'm just doing this because I've done it before and it worked well. So now I will paste the whole documentation here. TLDR code. And what it does basically, it restructures documentation in ways that make it really easy for an LLM to read it later. So basically it breaks everything into sections. These sections are like self-explanatory, kind of flat. There are hierarchies under them. If there's like sub stuff, as you can see, it's basically breaking down every element. Authentication is complex enough that it's a topic of its own, pagination the same. I'm just gonna wait it out for a little bit because I want to use this documentation to then give it back to GPT and tell it, please extract the information that I need for this. Yeah, it's probably gonna do some examples now because apparently it can use that. You can chat with GPT basically to ask it, hey, how do I create a good prompt? And then you can see if that actually happened. So this happened. I think it's fine. I'll just copy this into our document and reuse it. How do I copy this? Here. So I just put them here so I can reuse them later. Now I'm reverse prompting to give me this prompt for extraction. So please turn this into an extraction prompt. Is to extract all necessary from a document or code to create the RestAPI source. So sorry about that. I wasn't talking, but essentially you want to know, you wanted to flag if there's something missing, and you also wanted that is a structured JSON format. So like it's easy to read and work with. So let's do that. All right, it's going to tell us all the fields. So I love this because it's so explicit. It tells you, hey, look, everything, authentication, how does it work? Headers if necessary, paginator, resource defaults, so like primary keys, right dispositions. Let's see. Let's giving an example output. No, I wanted to run the extractor on an example. Yes, I do. Let's save this prompt. Because we will use it later. And now let's find some code. I was working earlier with Pipedrive. So let's see if we can find some code online. Here. Okay, so this seems to be a bunch of code. It's more code. Basically, I don't want to read this. So, yes, please try to extract from this. I'm just gonna give it all the code I find here. Let's see what happens. I honestly don't know. I've never done this before. I've tried other things. Okay, let's see. I have some doubts. I know that it doesn't know anything about Pipedrive really, so this is why I picked it. Or like it knows some things, but it's quite confused. So I think this might not be quite correct. Resources, it didn't get it. Okay, let's try another one. Let's take, for example, I think we can find some connector here. Pipedrive is common, so I expect it's in just about any connector catalog. We have it too. I'm just taking like something else. I think this might be it. Yeah, this looks like something we could use. Like there's some, I don't know, error byte configuration basically. So let's try. Actually, let me just save this document. Sorry, my Finder is throwing me. Ah, totally not it. Let's try again. Let's take our prompt. So let's see. Let's try again. Okay, this looks much better. This looks right. This could be a different column. I guess this could work too. This is correct. So the incremental was done correctly. Or at least extracted correctly. So yeah, that worked out. We could save this for later and use it. I would say let's leave it for now. One of the things I think what is missing is wait. Yes, this is just deals. And basically the other resources are missing, but I guess you could just like make the rest of them, and I don't really see where are the terms, items, deal. Yes, basically you could change this to the other endpoints as well to get them as well. But yeah, there are also, I think, some that might be full load only that are missing. So you wouldn't have all the, or like user details or stuff like that. Okay, James, can you just cut this short? Because I don't know what to say. But essentially, yeah, cut the gap. We have this extraction prompt. Now let's see how we can create a build prompt. So let's take our extraction prompt and tell it in the documentation. Okay, so now let's try to create a REST API source from this with the prompt. So let's get the prompt. Please make sure you use the and I tell it, please explicitly use that and don't write custom code. To reinforce, I'll give it once more the documentation. So I'll copy this out. To refresh its memory. So after we get all of these, we'll set up cursor and try it there because we want to be able to run the pipeline that is being built and understand how well this works and what we can do next. Okay, it gave us our build prompt. And let's just put it in here and review it. Weird. Okay, and now I'm telling it, please try to use the REST API declaratively first, because if we don't do that, GPT really likes to write code, and it will do that, and it will ignore our thing, and then it's going to be really hard to troubleshoot because it will do custom code. Okay, so we give it an example, and yeah, this should work. Okay, next I'm going to switch to cursor and show you how that should be set up to make this work. Alright, so let's see how we can apply that. And what I did so far is I installed cursor and I added a few things in here. So I have an old pipe drive script. I have this other connector from a different framework, but again, this won't have all the information because it's part of a framework, so it depends on the framework how it actually turns these YAMLs into code. Then we have actual documentation, so I configured this to add docs, and I added DLT hub docs, REST API docs, manually, and pipe drive, which is the pipeline that we'll use. And I added our two rules, one to create REST API and one to extract features. Okay, and this one applies to all requests actually. And this rule is actually an old one. Let me fix it. Let's put the one that we had, that we created earlier. Okay, now it has this build prompt that we had before with some code examples. And now let's try it. So I will add the documentation. And basically, because our REST API connector is just like a config, I won't do the extraction part separately because it just, you can see the same thing in our connector, and I'm a little bit more familiar with it personally. So let's get the pipe drive docs, and I think our rule is already there. It's always used. And let's add the documentation as well, just explicitly. I think we don't have to do it. It will just automatically detect what to use. But since I have lots of stuff here, it might get confused. So please read the pipe drive docs to build. So I'm asking now to create a separate pipeline. I have the thing in ask mode. That's not good. I actually need it to be in agent mode, because in ask mode it cannot create files. Okay, so this file is now created. Let's look at this. Yeah, this is right, I think. Yeah, and these are merged, but they could be just for load. Basically merge, what this means here is that if a record is no longer present in a new extract, it won't get deleted. So it's like preserve deletes. Okay, let's try to run this. I already have a try key in my DLT secrets file. Okay, and we already have a pipe drive key, but it's looking for a different name. It's looking for pipe drive API token. Fine. It just generated some different naming scheme. So I just put it there and try to run it again. Okay, something went wrong. So let's give it to our agent and see if it can fix it. Okay, so maybe that worked. It did not. Oh, right. Let's try to see again. Maybe it works. This is vibe coding, so I'm not actually coding. I'm just trying to get the LLM to code for me. And it looks like it worked this time. So we got some data out of it, as you can see. Okay, now let's try to build a different pipeline. So as you can see, it's possible from the docs as well. What happened here was it didn't do all the endpoints. So maybe I can try. Let's see. Let's see. So now I'm telling it, hey, can you add the rest of the endpoints? And for incremental, can you use recents and do a resource, like a DLT Hub resource for each entity we can request from it. But I don't know if it can do it. I don't know if it can process the docs. So let's see. So let's see what it did. I think it added some more entities: products, pipelines, stages, users, goals, metadata, DL fields. And this is custom fields, very useful, but we don't really load them this way. Recents, it's trying to get everything. This is correct since param, but it should be, I think. Yeah, this could work, but then the problem is this resource would return all these entities into one single table, so that wouldn't really work. But the increment is correct, so that's something. It's something. Okay, so now let's try if this could be fixed from other data sources. Actually, no, I don't think it needs another data source. I think this is just a misunderstanding of what I want. Split into many resources on for each item. So yeah, I mean, the naming is not great and we need to change it, but now it looks correct. So it's actually really nice. I would say it's quite nice. We don't actually even need the other endpoints, so we could just delete them. I'm surprised because I was trying this earlier and I tried with GPT. I tried also in GPT client directly. I also tried Perplexity and it couldn't process the pipe drive docs. So I wanted to basically demonstrate how it won't figure out the docs and eventually we can figure it out. And I guess it didn't because ultimately it solved some of the parts by taking information from responses. So I'm not entirely sure how much it solved which way. But I can also show you how you can modernize a legacy pipeline. So let's do that. Let's tell it, hey, look into my other stuff. So basically what I want to do here is call it like modernization of legacy. And it should load to iceberg if you know to do that, because DLT, if not, stick to DuckDB. I'm not sure the LLM will know how to do that because it's kind of like new for us. Okay, now it found the files. It found the files. And I think I just have like deals and partners or something. It's a few more things. Okay, so let's see what happened. This is hallucinated, I think, because we don't have a Hive catalog. And this is how you do it in DLT plus, not in DLT. But yeah. Let's tell it to fix that and let's see what else happened. Yeah, this is basically some artifacts from my legacy stuff because I was managing schemas directly in Python code or something like that. So this looks good, actually. Yeah, we have the deals, we have the organizations, yeah. Pipelines. And we have a way to update. Because, yeah, we did a full load from the other things and incrementing from these, as far as I remember. Yeah, so that works as well. So now that you kind of understand how to approach this problem and how to troubleshoot it, I strongly encourage you to vibe code. It only takes you maybe 1 hour to do an experiment, and I think you'll be so impressed that you will really like it. And to be honest, I think that coding these types of pipelines might literally go away not too far in the future if we manage to, let's say, create good technical systems to help us iterate through the rules, just like we did here manually. And really, I think what we need to consider is not just how we do an integration, but how the information that we create and capture during this integration can be propagated downstream. So we actually automate much more than just, do the first step and then repeat everything on the transformation and then have new logic on the semantic layer, where we could, in theory, declare lots of the information up front, generate the rest of the code. And we actually can do that with DLT-DBT generator or DLT SQL mesh generator. You can look them up. And then, do, let's say, new things or new automations, or even maybe going from here to I have my data in the database to modeling can be a very interactive and declarative experience. But like I said, this can only be really if we consider the metadata handover from the original creation all the way downstream. Otherwise, we'll just have to repeat this over and over. So this is the end of our course, and I want to leave you with 3 call to actions. The first one is to keep learning. So try to make education a constant part of your career. What I mean is I regularly tell my employees to take 20% of their time for learning, because this makes them better professionals. Now, of course, you can judge for yourself how much time you have to invest, but essentially the more you learn, the more effective you become and the happier you become, because you find better ways of doing things so you don't have to suffer through all the bad practices. My second call to action is, if you're learning, be social about it and encourage others. So when you learn something, implement it, because actually typing it in and implementing it makes it real in your head, makes it happen. This is how you learn best. And once you've done that, share it with others, so others can also get motivated and understand how you're approaching things. There's also imposter syndrome, so if others see how simple it is to do and what you're actually doing, this will encourage them. And my final call to action is, and of course, tell us if you do any personal projects with DLT. It would be cool to reshare them. And the final call to action is, if you want to learn more with DLT, we actually have a courses repository on our GitHub. So if you go to our GitHub organization, you can find an education repository, or you can go to our website to events. And there we have an education newsletter. So you can just sign up for that. And every time we do an educational event, you'll get an email. So for example, it could be some kind of workshop, or it could be a course like this one. That being said, I thank you for taking this course, sticking with me all throughout, and I hope to see you in other educational content.